All right. Okay, let's not do that. All right, we're going through the art of computer programming from start to finish. It's going to take a while. So we're going to see how it goes. When I say a while, I think it's probably going to take a number of years. So it'll be something kind of interesting to work through on stream is my hope. It'll also be pretty difficult because it's pretty difficult work. And the reason I've chosen it is because it's one of those books that everyone, like, it's a book that you're supposed to have on your bookshelf, but that very few people have actually read through all of. And I'm going to try and be the exception to that and actually read through it. Hello, Uman Ra. Hello. So I'm going to try to work through it. We're going to work through it from start to finish. We're not going to do all the exercises first time round because I'm not good enough to do that. But we will get through a lot of them, get through some of them anyway, and we'll go back to some of them. And there's also going to be quite a lot of prerequisite work, and there'll also be quite a lot of me getting stuck as well, which will be thrilling viewing, I'm sure. I think with this, so this is the first edition. It's, paid for. I have bought it. I spent my own money. Well, I spent company money on this, and it's so it's I'm not pirating it, and I haven't spent loads of time preparing for what I'm going to need to know, but I have glossed the first chapter or two, and it's going to get pretty. So Knuth does he as you'll see in the first chapter, which we're going to go through at the introduction, he talks a fair bit about how the math is not necessarily required to work through and gain benefit from the book, which may be true, but it gets pretty mathy pretty soon. And so my suspicion is that we will probably get through, and I will hold my hands up and I will say I do not know very much mathematics, and that will be an issue fairly quickly. So I think probably certainly by the end of the first section, the first proper section, I'm going to go and have to do some math study as well, which I will do also on stream. Part of the idea of this is to try to capture this activity and see what it actually takes to read this whole book and then, to some extent understand everything that Knuth is trying to say in it. It's supposed to be a classic. It's labeled a classic. So we're going to experience what a classic work in computer science is. So, The Art of Computer Programming, it comes in a number of volumes. It's not finished yet. Knuth is in his 80s, and he's working on, I think, the third sub-volume in the fourth volume. And I think there's supposed to be like 7... I think there's supposed to be 5 volumes, maybe. I don't know exactly how many there are. In any case, it's not done yet. So it will change as we work through it. And we may finish it before he does. Or he may finish it before we do. In any case. So, Art of Computer Programming, Volume 1, Fundamental Algorithms, 3rd edition. There are 2 prior editions. There is a little funny quirk in the 1st and 2nd editions, which I will point out when we get there. This series of books is affectionately dedicated to the Type 650 computer once installed at the Case Institute of Technology in remembrance of many pleasant evenings. So I think he originally started working on this in... Let's look this up. I think it was the 60s. Yeah, the first one was published in 1968, and so the Type 650 computer, I guess it's probably the IBM 650 he's talking about. Let me just get a photo of that. and we can look at it. Yeah, so looks like this. I guess he had plenty of pleasant evenings with this. I think it is anyway. I mean, I guess there could be other computers labeled 650. But this is probably the prime candidate. Here's an interesting photo. Let me share this photo as well. So I guess it's oh yeah, sorry. Guess it's back in the time when you would have to I have not used a computer like this, but my understanding is that you would set the memory in some sense by tweaking these dials and I guess hitting a go button to insert something, and you'd have to, I guess he's going through here. He's going through a flow chart, so I suppose he must be code. Oh no, he's got a listing here. So he's probably this guy is probably not Knuth. This is not Knuth, pretty sure. Yeah, he's probably putting in a program, or maybe he's looking at some results or something like that. So I suppose this would have been the very pleasant time that Knuth was having with his computer back in the day. So not so much. There was no notifications on this computer. Fortunately, well, I guess there were, but they were the ones you cared about. He's at Stanford, Knuth. I believe I'm pronouncing his name correctly. I've been corrected on that once before, but I think it's Knuth, spelled like canoe. That was a comment somebody left somewhere. Now, one of the funny things about Knuth's career is that, let me just make sure I'm sharing the right thing. Oh, wow. Jan Shufim, you started working through Art of Computer Programming yourself recently. How far are you through? How's it going? So Knuth, he started this project. Well, he published the first edition I think in 1968. And then he started work on the second edition directly after, but he felt that at that time there was no appropriate typesetting system that he could use for his work. And as a result, he took a 10-year break from writing these books, which he's still writing, in order to produce the TeX, currently probably known better as LaTeX, publishing system or typesetting system, and then went back to working on his books using that software. So as a side effect of his work, we now have the main kind of technology used for typesetting academic works and probably some other works too, which is kind of, it's a bit of a flex, I guess. If only all of our side projects could have that kind of result, or maybe it's best they don't. Okay, so I'm mostly just going to read a lot of this. I'm not committing to reading it all out. Like, I don't want to be like a total audiobook exactly, but I guess part of this is reading it through. Would encourage you to buy the book and follow along yourself. Buy the books and follow along yourself if you can afford it, and if it will benefit you. Jan Shufim, about 130 pages in, where he starts describing a custom assembly language. Yeah, the mix language. I'm more of a mathematician than a programmer by training, and I'm slowly making the move across. So I skimmed the maths and I'm taking my time over the programming. Well, it will be the opposite for me. Yeah, interesting. He one of the things that will come up in this process is there's Mix, which is the original assembly language for the virtual computer that he developed for this book to explain algorithms, and then there's, I don't know how it's pronounced, Mix, 2 M's, and that's the new one that he views to be like more modern. And then there's he updated, he made an updated version of like he made a supplement to the first edition himself, which was for Mix. And then there is an extra book which is like a translation layer between the first 3 editions and the mmix versions. I'm not like 100% sure how I'm going to handle that yet. It feels like a bit of a work, it's in the process of migrating, but I have purchased all the supplements, so we will get to compare when we get to those points and see what the differences are. I'm personally kind of inclined to do it in the first version because I think I'm kind of interested in the original work, but I know Knuth will probably say mmix would be better, so I'll probably do both. I'll probably also be developing some custom tools for that language in the process. There is a GNU version of mix, but well, I think it'd be interesting to have something more visual to show on stream, I suppose. So I'll probably make an ID or something, the same thing I did with Fourth. Tiny CLJ. Funny enough, I thought about AOCP and trying to work through it myself, but did not follow up on the idea, knowing to what depth Knuth tackles problems. Yeah, a common sentiment about the books is I have them. I started to work through them and then I didn't. So we'll see whether I fall into the same thing. But my intention is to try to persevere and get through all of it, even though I have no business really doing so. I will need to do quite a lot of learning to be able to get through it. Even the end of the first chapter is the end of the preface is pretty funny. It's not funny, but it's pretty funny. Okay, anyway, let's lock in. Preface. Here is your book, the one your thousands of letters have asked us to publish. It has taken us years to do, checking and rechecking countless recipes to bring you only the best, only the interesting, only the perfect. Now we can say without a shadow of a doubt that every single one of them, if you follow the directions to the letter, will work for you exactly as well as it did for us, even if you have never cooked before. McCall's Cookbook, 1963. There's quite a lot of these little epigraph type things strewn throughout, and I'm going to try and look them up at various points. We'll come back to that one. I haven't looked that one up yet, but I guess it's a cookbook. The analogy, I suppose, is that Knuth is trying to claim that this is some sort of cookbook. Now there is a let's say a common view that Knuth's books are intended to be used as reference books, and a lot of people use them that way, and I think that's probably fine. However, in the preface, despite this little cookbook type intro, he does seem to be indicating that this is a book that he is designing to be read from start to finish, which is sort of interesting. And part of the things that's interesting about this work is that it clearly it's a textbook. It's a narrative textbook with the same scope as a reference work, which is like almost. I mean, it's no surprise he hasn't finished it after literally working on it since the 60s. Okay, the process of preparing programs for a digital computer is especially attractive, not only because it can be economically and scientifically rewarding, but also because it can be an aesthetic experience, much like composing poetry or music. This book is the first volume of a multi-volume set of books that has been designed to train the reader in various skills that go into a programmer's craft. Now, worth noting, though this is a later edition, it's worth noting this word programmer. This highlighting will become irritating very quickly. This word programmer, now back in the day, there was a distinction between the word programmer, I believe, and there was a distinction, I think, between programming and coding, maybe? There wasn't software engineering yet. I believe the work of the programmer was the work of designing the algorithms into essentially a form of flowchart, and the work of the coder was then, actually putting this into some sort of machine code that can execute, and then putting this into the computer. So these were separate works, and they were also, I believe, although if this was in a main channel video, I would research this more thoroughly. I believe that it was also gendered work, so it would often be men who were doing the programming part and women who were doing the coding part, because the coding was seen as more administrative, I suppose, at that time. Now that's totally not how it was for every person, but that's my current understanding of what that was like. Yanshifim, agreed. I don't think Knuth is writing them as reference books, even though I think most people use them that way. Yep, that's the impression I've got as well. Lazy Schema, hi. Are you a fan of the Schema books, Lazy Schema, or is that a coincidence? I'm very well, thank you. Good to hear you in the chat. Yeah, I'm very well. I had a haircut today, and I planned my haircut specifically because I was going to be starting these streams, and my hair was like too long, like horrendous. But of course, the day after, you go into at least for me, I go into the hairdressers. I go in there, I want my hair cut right, and then they spend half the time cutting the hair and half the time like styling it. So I knew that it would look like a bit. I always feel like it was a bit poodly at this point. So I thought about washing it out, but I'd already had my hair washed like 3 times that day, so I was like not doing that. Other than that, I'm pretty good. Yeah. Oh, that's the inspiration. Oh, cool. Yeah, I think I've got some of those books somewhere. I've got one about like they did an AI one back when AI was not totally Transformers. Or maybe no, it was Transformers actually. I think it was Transformer based. And I got through about half of it, but I didn't get through all of it. But yeah, nice books. I've not read the Scheme ones though, although I have used Scheme as part of those books. Yes, anyway. So Programmer's Craft, which I suppose we can assume he's probably talking about the design of algorithms as opposed to the writing of code necessarily here, which makes sense with his view on the book as being about the analysis of algorithms. The following chapters are not meant to serve as an introduction to computer programming. The reader is supposed to have had some previous experience. The prerequisites are actually very simple, but a beginner requires time and practice in order to understand the concept of a digital computer. The reader should possess some idea of how a stored program digital computer works, not necessarily the electronics, rather the manner in which instructions can be kept in the machine's memory and successfully executed. Okay, I think I've got that. It's interesting to note that in these kind of points, just compare this to how you would think about like somebody, like I think he's how does he phrase this? The prerequisites are actually very simple, but a beginner requires, etc., etc., etc. Yeah, some previous experience. Just compare this to what you think some previous experience is in the context of your everyday life. So, some idea of how a stored program digital computer works, an ability to put the solutions to problems into such explicit terms that a computer can understand them, quotes. These machines have, this is funny, these machines have no common sense. They do exactly as they are told, no more and no less. This fact is the hardest concept to grasp when one first tries to use a computer. Now, this is no longer true, right? I can get my, $2.56 right now on the first page by saying this is no longer true, because we now, computers can now do this as of the past few years. They do have something like common sense, although it might not be exactly as he meant it here. I recently came across a paper that Knuth had written recently. I think even this year, it was February this year, I think that he wrote it, where he was remarking on the fact that an open problem he was working on has recently been solved by somebody, essentially a person using, I think it was, the latest Claude and OpenAI models. And he was sort of, I suppose he started off somewhat, not necessarily skeptical, but he didn't think that we were at that point. And so he wrote up the proof in a paper and credited, of course, the people who worked with the AI themselves in order to come up with it. And it's, what a fascinating life he has lived, to live until the point where he's able to see this all the way from, what we see now on the screen, this computer at the start. And looking at this paragraph also, it makes me wonder, because in my mind, basically, here's when I read this paragraph, in my mind, what I thought is that it's kind of a boomer take. Like, I guess it's a bit derogatory, but I don't mean it so derogatively. People used to say to me, when I was younger, computers just do exactly what they're told. That's the main thing you need to understand. And I was like, obviously that is the case. It's not surprising or at all hard to understand. They are machines. They're not going to, they've not got no imbued ability to work out intention in the same way that a person or an animal would. So it's not the hardest concept to grasp when one first tries to use a computer, in my view. But maybe at the time that this was written, lots of people did struggle with that idea. Maybe possibly people still do. I would imagine that they probably don't as much. But maybe if you grew up in a world without computers of this nature, then it would seem like computers, in I think Dan Bricklin's terms, could just, they know the future. So it's not surprising if they can do things like work out what you mean, although they now can. So maybe it would be we've gone from an era where people did sort of assume computers would work out what you meant to one where that was not the case, and people assumed computers knew nothing and they were just, dumb machines, to now maybe a world in the future where that idea will be lost again, and we will think of computers in a much more amorphous or intelligent way. I don't know, but I kind of stumbled on this paragraph. Yeah, he is definitely talking about that lazy schema, about how people get surprised about the computer can't even work out what they meant despite a typo. But I never found that particularly startling, I guess, and I've not known that many people to find it startling actually in the modern times. But maybe it was more true back then. Okay, C, some knowledge of the most elementary computer techniques, such as looping, performing a set of instructions repeatedly, the use of subroutines, and the use of indexed variables, to which I assume he means like arrays. I don't actually know exactly what he means by indexed variables, but I believe he probably means arrays. So it's like a location memory you can add an index to get a particular item from a particular memory cell. That's my assumption. D, a little knowledge of common computer jargon, memory, registers, bits, floating point, overflow, and software. Most words not defined in the text are given brief definitions in the index at the close of each volume. These 4 prerequisites can perhaps be summed up into a single requirement: that the reader should already have written and tested at least, say, 4 programs for at least one computer. This is a funny paragraph, because at the time, writing 4 programs would be a significant amount of work, and at least one computer, you would need to rewrite your program for any new computer you were working on, any new type of computer, let's say. So for the IBM 600, you write a computer program, it would be a fairly big task. And then maybe if you want to work on another computer from a different manufacturer, you would need to write it again. And this would be a very routine task because we didn't have high-level languages that would compile into machine code in the same way that we do now. Like there were emerging techniques, but it was not a thing you could rely on existing. I've tried to write this set of books in such a way that it will fill several needs. In the first place, these books are reference works that summarize the knowledge that has been acquired in several important fields. In the second place, they can be used as textbooks for self-study or for college courses in the computer and information sciences. To meet both of these objectives, I have incorporated a large number of exercises into the text and have furnished answers for most of them. I have also made an effort to fill the pages with facts rather than with vague general commentary. This set of books is intended for people who will be more than just casually interested in computers, yet it is by no means only for the computer specialist. Indeed, one of my main goals has been to make these programming techniques more accessible to the many people working in other fields who can make fruitful use of computers, yet who cannot afford the time to locate all of the necessary information that is buried in technical journals. A very different world he was talking about there. We might call the subject, and this is a really interesting paragraph because it represents a real departure from what computers have been used for up until now. We might call the subject of these books non-numerical analysis. Computers have traditionally been associated with the solution of numerical problems, such as the calculation of the roots of an equation, numerical interpolation, and integration, etc. Or, for example, working out how running simulations to do with nuclear weapons, as the original computers were used for, or for cracking the Enigma code, stuff like that. War purposes, I suppose, war mathematics. But such topics are not treated here except in passing. Numerical computer programming is an extremely interesting and rapidly expanding field, and many books have been written about it. Since the early 1960s, however, computers have been used even more often for solving problems in which numbers occur only by coincidence. The computer's decision-making capabilities are being used rather than its ability to do arithmetic. So I guess computers as decision-making tools, which it's not necessarily easy for me to pinpoint exactly what he's talking about there, because we're talking about a world that Knuth is talking about beyond simply calculating like the answers to numerical questions, but also before, like meaningfully before, I would say, the graphical user interface and the personal computer. So there was something in the middle, presumably still academic or military or maybe in business terms, that was being done here. Maybe he was talking about business computing, I don't know. But we certainly weren't talking about the sorts of computer programs that we're operating with today to kind of run our lives and, engage with, each other on Twitch and such. So he's got he's at a middle point in history, which is interesting. We rarely feel a need for we have some use for addition and subtraction in non-numerical problems, but we rarely feel any need for multiplication and division. Of course, even a person who is primarily concerned with numerical computer programming will benefit from a study of the non-numerical techniques, for they are present in the background of numerical programs as well. The results of research in non-numerical analysis are scattered throughout numerous technical journals. My approach has been to try to distill this vast literature by studying the techniques that are most basic, in the sense that they can be applied to many types of programming situations. I have attempted to coordinate the ideas into more or less of a theory, as well as to show how the theory applies to a wide variety of practical problems. So I suppose he's saying that he has a central theory in these works, which is interesting. I wonder what that is. Of course, non-numerical analysis is a terribly negative name for this field of study. It is much better to have a positive, descriptive term that characterizes the subject. Information processing is too broad a designation for the material I'm considering, and programming techniques is too narrow. Therefore, I wish to propose analysis of algorithms as an appropriate name for the subject matter covered in these books. The name is meant to imply the theory of the properties of particular computer algorithms. The complete set of books, entitled The Art of Computer Programming, has the following general outline. Volume 1, Fundamental Algorithms. Chapter 1, Basic Concepts. Chapter 2, Information Structures. So that's the volume we're on right now. Volume 2, Semi-Numerical Algorithms. I'm not sure, maybe that still is the title. Composed of random numbers and arithmetic. Sorting and searching, composed of sorting and searching. Combinatorial algorithms, composed of combinatorial searching and recursion. And syntactical algorithms, composed of lexical scanning and parsing. Now, I believe he has not yet started volume 5. He is working on volume 4, I think chapter 7. I don't think he's gotten to recursion yet, and I think he may have expanded chapter 4, as this is the one which ends up with multiple volumes. And indeed, he goes into this here. Volume 4 deals with such a large topic, it actually represents several separate books, volumes 4A, 4B, and so on. 2 additional volumes on more specialized topics are also planned. So he's got even more. Volume 6, The Theory of Languages, and Volume 7, Compilers, these making up chapters 11 and 12. I started out in 1962 to write a single book with this sequence of chapters, but I soon found that it was more important to treat the subjects in depth rather than to skim over them lightly. The resulting length of the text has meant that each chapter by itself contains more than enough material for a one-semester college course, so it has become sensible to publish the series in separate volumes. I know that it is strange to have only 1 or 2 chapters in an entire book, but I have decided to retain the original chapter numbering in order to facilitate cross-references. A shorter version of volumes 1 through 5 is planned, intended specifically to serve as a more general reference and/or text for undergraduate computer courses. Its contents will be a subset of the material in these books, with more specialized information omitted. If we ever get that, I will be amazed. The same chapter numbering will be used in the abridged edition as in the complete work. The present volume may be considered as the intersection of the entire set, in the sense that it contains basic material that is used in all the other books. Volumes 2 through 5, on the other hand, may be read independently of each other. Volume 1 is not only a reference book to be used in connection with the remaining volumes, it may also be used in college courses for self-study as a text on the subject of data structures, emphasizing the material of Chapter 2, or as a text on the subject of discrete mathematics, emphasizing the material of sections 1.1, 1.2, 1.33, and 234. Or as a text on the subject of machine language programming, emphasizing the material of sections 1, 3, and 4. Not very interesting. Not the topic, but this passage. The point of view I've adopted while writing these chapters differs from that taken in most contemporary books about computer programming, in that I am not trying to teach the reader how to use somebody else's software. I am concerned rather with teaching people how to write better software themselves. The original goal was to bring readers... Oh, okay, don't want to do that. The original goal was to bring readers to the frontiers of knowledge in every subject that was treated, but it is extremely difficult to keep up with a field that is economically profitable, and the rapid rise of computer science has made such a dream impossible. The subject has become a vast tapestry with tens of thousands of subtle results contributed by tens of thousands of talented people all over the world. Therefore, my new goal has been to concentrate on classic techniques that are likely to remain important for many more decades, and to describe them as well as I can. In particular, I have tried to trace the history of each subject and to provide a solid foundation for future progress. I have attempted to choose terminology that is concise and consistent with current usage. I have tried to include all of the known ideas about sequential computer programming that are both beautiful and easy to state. I believe he spends quite a bit of time on the history of things as well. A few words are in order about the mathematical content of this set of books. The material has been organized so that persons with no more than a knowledge of high school algebra may read it, skimming briefly over the more mathematical portions. Yet a reader who is mathematically inclined will learn about many interesting mathematical techniques related to discrete mathematics. This dual level of presentation has been achieved in part by assigning ratings to each of the exercises so that the primarily mathematical ones are marked specifically as such, and also by arranging most sections so that the main mathematical results are stated before their proofs. The proofs are left either as exercises with answers to be found in a separate section, or they are given at the end of a section. A reader who is interested primarily in programming rather than in the associated mathematics may stop reading most sections as soon as the mathematics becomes recognizably difficult. On the other hand, a mathematically oriented reader will find a wealth of interesting material collected here. Much of the published mathematics about computer programming has been faulty, and one of the purposes of this book is to instruct readers in proper mathematical approaches to this subject. Since I profess to be a mathematician, it is my duty to maintain mathematical integrity as well as I can. A knowledge of elementary calculus will suffice for most of the mathematics in these books, since most of the other theory that is needed is developed herein. However, I do need to use deeper theorems of complex variable theory, probability theory, number theory, etc. at times, and in such cases I refer to appropriate textbooks where those subjects are developed. The hardest decision I had to make while preparing these books concerned the manner in which to present the various techniques. The advantages of flowcharts and of an informal step-by-step description of an algorithm are well known. For a discussion of this, see such and such article in ACM. Yet a formal precise language is also necessary to specify any computer algorithm, and I needed to decide whether to use an algebraic language such as Algol or Fortran. So Algol's kind of, let's say it's a precursor to C, and I suppose Fortran is kind of as well, although Fortran's kind of still used for maths stuff. Or to use a machine-oriented language for this purpose. Perhaps many of today's computer experts will disagree with my decision to use a machine-oriented language, but I've become convinced that it was definitely the correct choice for the following reasons. I think here he may be obliquely referring to, and I'm not sure about the timeline of this, but I'm wondering whether he's referring to Dijkstra. Edgar Dijkstra had a big view that learning about computing should stem from the abstract first and not from the machine. So using a machine language is not a good idea for teaching programming. But I'm not actually sure if he's referring to that here. Maybe it would have been a general view at the time, though it seems funny now. For the following reasons. A programmer is greatly influenced by the language in which programs are written. There is an overwhelming tendency to prefer constructions that are simplest in that language rather than those that are best for the machine. By understanding a machine-oriented language, the programmer will tend to use a much more efficient method. It is much closer to reality. The programs we require are, with few exceptions, or rather short, so with a suitable computer, there will be no trouble understanding the programs. High-level languages are inadequate for discussing important low-level details such as coroutine linkage, random number generation, multi-precision arithmetic, and many problems involving the efficient usage of memory. A person who is more than casually interested in computers should be well schooled in machine language, since it is a fundamental part of a computer. Some machine language will be necessary anyway as output of the software programs described in many of the examples. I seem to remember actually that the mix language, the one which is used in these books and which is different from the one that is Knuth's preferred language now, uses also self-modifying code, which is kind of cool. And I suppose it would be difficult to understand the algorithms unless they were written in machine code in some sense. And the final point, new algebraic languages go in and out of fashion every 5 years or so, while I am trying to emphasize concepts that are timeless. From the other point of view, I admit that it is somewhat easier to write programs in higher level programming languages, and it is considerably easier to debug the programs. Indeed, I have rarely used low-level machine language for my own programs since 1970, now that computers are so large and so fast. So I guess he's writing this. I probably should have assumed this anyway. I don't actually know when he was writing this particular preface. It could have been quite a bit later. I don't know if that's put anywhere. I think he updates this particular preface. Would need to check that. Now that computers are so large and so fast, again, this is before personal computing, so I suppose it would have been post. He would have had access to computers beyond the 650, which we can see here, but there weren't personal computers yet, I suppose, or at least they weren't around commonly enough that he would have revised this to say computers at least are not so large as they once were. Maybe he's talking about memory space. No, I mean, I think he's generally talking about the size of the computer. Many of the problems of interest to us in this book, however, are those for which the programmer's art is most important. For example, some combinatorial calculations need to be repeated 1 trillion times, and we save about 11.6 days of computation for every microsecond we can squeeze out of their inner loop. Similarly, it is worthwhile to put an additional effort into the writing of software that will be used many times each day in many computer installations, since the software needs to be written only once. By the way, there is a very small, hopefully, sound bed on this stream of some rain somewhere, I think, in case you're wondering why it's raining. Keeps me focused. Given the decision to use a machine-oriented language, which language should be used? I could have chosen the language of a particular machine X, but those people who do not possess machine X would think this book is only for X people. Furthermore, machine X probably has a lot of idiosyncrasies that are completely irrelevant to the material in this book, yet which must be explained, and in 2 years the manufacturer of machine X will put out machine X+1 or machine 10X, and machine X will no longer be of interest to anyone. So I suppose he's been proven right there. To avoid this dilemma, I have attempted to design an ideal computer with very simple rules of operation, requiring, say, only an hour to learn, which also resembles actual machines very closely. There is no reason why a student should be afraid of learning the characteristics of more than one computer. Once one machine language has been mastered, others are easily assimilated. Indeed, serious programmers may expect to meet many different machine languages in the course of their careers. Or none. So the only remaining disadvantage of a mythical machine is the difficulty of executing any programs written for it. Fortunately, that is not really a problem, because many volunteers have come forward to write simulators for the hypothetical machine. Such simulators are ideal for instructional purposes since they are even easier to use than a real computer would be. I have attempted to cite the best early papers in each subject, together with a sampling of more recent works. When referring to the literature, I use standard abbreviations for the names of blah, 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 blah. He lists them out as an example. He has a book called Concrete Mathematics, which we will certainly spend some time with in the course of this project. Much of the technical content of these books appears in the exercises. When the idea behind a non-trivial exercise is not my own, I've attempted to give credit, corresponding references, etc. This is not very interesting. I've of course received assistance from many people during the years I've been preparing these books, for which I'm extremely thankful. Acknowledgements are due first to my wife Jill, for her infinite patience, and for preparing several of the illustrations, and for untold further assistance of all kinds. There's Robert W. Floyd, thousands of other people, research, National Science Foundation and the Office of Naval Research, Addison Wesley, etc. In another preface, he's spent some time developing tech. Yes, okay, let's read this part. This is interesting. After having spent 10 years developing the tech and metafont systems for computer typesetting, I am now able to fulfill the dream that I had when I began that work by applying those systems to the art of computer programming. At last, the entire text of this book has been captured inside my personal computer, so he now has personal computers, in an electronic form that will make it readily adaptable to future changes in printing and display technology. The new setup has allowed me to make literally thousands of improvements that I've been wanting to incorporate for a long time. You can imagine the amount of difficulty he would have had editing this book prior to computing, in particular personal computing and a typesetting system. In this new edition, I've gone over every word of the text, trying to retain the youthful exuberance of my original sentences while perhaps adding some more mature judgment. Dozens of new exercises have been added. Dozens of old exercises have been given new and improved answers. The art of computer programming is, however, still a work in progress. Therefore, some parts of the book are headed by an under construction icon, which makes me laugh. It feels very like Web 1.0, to apologize for the fact that the material is not up to date. My files are bursting with important material that I plan to include in the final glorious 4th edition of Volume 1, perhaps 15 years from now. But I must finish Volumes 4 and 5 first, and I do not want to delay their publication any more than absolutely necessary. Again, we may never see this update. My efforts to extend and enhance these volumes have been enormously enhanced since 1980. So he wrote this he wrote this in 97. 1980 by the wise guidance of Addison Wesley's editor Peter Gordon. He has become not only my publishing partner but also a close friend, while continually nudging me to move in more fruitful directions. Indeed, my interactions with dozens of Addison Wesley people, I guess this is his publisher, during more than 3 decades have been much better than any author deserves. The tireless support of managing editor John Fuller, whose meticulous attention to detail, blah, 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 hard work, new edition accomplished by various people, converted illustrations to meta post or something, mistakes, tried to avoid introducing new errors. However, I suppose some defects still remain and I want to fix them as soon as possible. Therefore, I will cheerfully award $2.56 to the first finder of each technical, typographical, or historical error. The web page cited on such a page includes a current listing of all corrections that have been reported to me. And we've got a little quote from Bill Gates there. Things have changed in the past 2 decades. So this is written in 97 in California. Okay. This is I should pause here and check chat. I'll do that. Film software and registers. Seeing software and registers as if they are similar levels of concept is very jarring in the model day. Yeah. Producer Matt Zachtronics taught a beginning programming class, and he said the biggest hurdle to teach was what Lazy Skimmer mentioned. Things like typos, quotations. Yeah, became a huge fan of Scratch-style block programming languages. Yeah, I mean, they definitely make mistakes like that. They definitely make mistakes. My hunch is that by theory, he means something more like abstraction. Interesting. Yeah, that's an interesting idea. Which is more like the way mathematicians use the word. Yeah, interesting point. Does algebraic or machine-oriented mean something like high-level, low-level? Yeah, it could do, actually. Yeah, I suppose it does. He's talking about Fortran being algebraic and ALGOL, which stands for, I guess, algorithm language being more algebraic. I suppose that's true. Yeah, and there was a lot of talk, which I've done some research in this area about the journey really from having a machine language, which they often they complained about having to address memory quite a lot, and so there's a paper by somebody called an addressless coding scheme or something like that, and they're trying to put mathematical expressions and have them be executed directly. So I suppose that is, yeah, that's probably exactly what he means. Mix has taken me 10 hours so far and I'm still struggling. Yeah, well, I'm sure I will commiserate with you when I'm there. Hello, Atom Fighter 10101. Thank you. I'm really glad you like the videos. I'm working on some more, but they are bigger. Classic YouTuber thing to say. But I am. So that's the truth. That's the truth of it. But thank you. Okay, so we've got this this algorithm here, I suppose. This flowchart. Very common to express algorithms in flowcharts back in this era. Fortunately, I think Knuth does not do a lot of it, although he does do it here. Because flowcharts are a little dated these days, I think, at least for practicing programmers. Now, I'm actually so unfamiliar with flowcharts that I recoil even looking at this. So I'm just going to go to the text description. So he has a procedure for reading these books, which is sort of funny. It's funny, one, because it's funny, just funny to start with, but it's also funny because it also expresses some of the problems that algorithms have, which you may see as we go through it. I'm going to go through it and then I'm going to explain, I think, what is going on here. So at first, we begin reading this procedure. Unless you've already begun to read it, continue to follow the steps faithfully. The general form of this procedure and its accompanying flowchart will be used throughout this book. 2. Read the notes on exercises on these pages. 3. Set n equal to 1. N is a variable I suppose we keep in our heads or something. Begin reading chapter n. Do not read the quotations that appear at the beginning of the chapter, for some reason. Is the subject of the chapter interesting to you? If so, go to step 7. If not, go to step 6. So if it is interesting to us, so let's say if it's not interesting to us, we go to step 6. Is n less than or equal to 2? If not, go to step 16, which I guess is us moving on. Yeah. If it is less than or equal to 2, scan through the chapter anyway, because chapters 1 and 2 contain important introductory material and also a review of basic programming techniques, and you should at least skim over the sections on notation and about mix. I suppose we don't have a point. We don't. What happens after step 6 actually? 6. So if 6, we go to 7. Otherwise, we increase n or something. 7. Begin reading the next chapter of the. Begin reading the next section of the chapter. If you've already reached the end of a chapter, however, go to step 16. Is the section number marked with an asterisk? If so, you may omit this section on a first reading. So we know that an asterisk is to tell us that this is a specialized topic that is interesting but not essential. I'm not quite sure exactly what we'll do with those. We'll have to make a note to come back to them if we do skip them. Are you mathematically inclined? If math is all Greek to you, go to step 11. Otherwise, proceed to step 10. Let's say we go to 10. Check the mathematical derivations made in this section and report errors to the author. Otherwise, if the current section is full of mathematical computations, you had better omit reading the derivations. However, you should become familiar with the basic results of the section. They are usually stated near the beginning or in slanted type right at the very end of the hard parts. We work the recommended exercises in the section in accordance with the hints given in the notes on the exercises, which you can read in step 2. After you have worked on the exercises to your satisfaction, check your answers with the answer printed in the corresponding section at the rear of the book, if any answer appears for that problem. Also read the answers to the exercises you did not have time to work. Note, in most cases it is reasonable to read the answer to exercise n before working on the exercise n+1, so steps 12 to 13 are usually done simultaneously. Are you tired? If not, go back to step 7, so we loop round. If we are tired, go to sleep, then wake up, then go back to step 7. Increase n by 1. If n is 3, 5, 7, 9, 11 or 12, begin the next volume in the set of books. If n is less than or equal to 12, go back to step 4. Congratulations. Now try to get your friends to purchase a copy of volume 1 and to start reading it. Also go back to step 3. So step 16, I had to really puzzle over what on earth was going on there. What are these numbers about? Is there some sort of jumping between the volumes thing that goes on? But there is not. Each book, one of the purposes of each book, maintaining the same numbering of chapters. So chapters 1 and 2 are in the first book, chapters 3 and 4 are in the second book, is so that this algorithm works, I suppose. So this chapter 3 is the last chapter in this book, and so we will move on to the second book at that point. So basically he's telling us to work through the book roughly in order and to skip the parts we're not interested in, and to do skip some of the maths if we want to or not, and take breaks and stuff like that. So it's that type of thing. And also chapters 1 and 2 are important, which is when put as an algorithm, somewhat hard to pass through. You got to do a bit of reverse engineering in your mind to work out what he's talking about, or at least I did. Then we've got some quotes. Woe be to him that reads but to one book, from George Herbert. I don't know French, but there's les milieux auteurs, parlant trop. Don't know. Books are a triviality, life alone is great, from Thomas Carlyle. This presumably has some meaning to Knuth. All right, let's work through this exercises part, because this brings us to the end of I think of the preface, and then it's to the contents. Okay, notes on the exercises. The exercises in this set of books have been designed for self-study as well as for classroom study. It is difficult, if not impossible, for anyone to learn a subject purely by reading about it without applying the information to specific problems and thereby being encouraged to think about what has been read. Furthermore, we all learn best the things that we have discovered for ourselves. Therefore, the exercises form a major part of this work. A definite attempt has been made to keep them as informative as possible and to select problems that are enjoyable as well as instructive. In many books, easy exercises are found mixed randomly among extremely difficult ones. A motley mixture is, however, often unfortunate because readers like to know in advance how long a problem ought to take. Otherwise, they may just skip over all the problems. A classic example of such a situation is the book Dynamic Programming by Richard Bellman. Richard Bellman really catches some strays at this point. This is an important pioneering work in which a group of problems is collected together at the end of some chapters under the heading Exercises and Research Problems, with extremely trivial questions appearing in the midst of deep unsolved problems. It is rumoured that someone once asked Dr. Bellman how to tell the exercises apart from the research problems, and he replied, "If you can solve it, it is an exercise. Otherwise, it's a research problem." Good arguments can be made for including both research problems and very easy exercises in a book of this kind. Therefore, to save the reader from the possible dilemma of determining which are which, rating numbers have been provided to indicate the level of difficulty. These numbers have the following general significance. 0, 0 is an extremely easy exercise that can be answered immediately if the material of the text has been understood. Such an exercise can almost always be worked in your head. 10, a simple problem that makes you think over the material just read, but is by no means difficult. You should be able to do this in 1 minute at most. Pencil and paper may be useful in obtaining the solution. 20. An average problem that tests basic understanding of the text material, but you may need about 15 or 20 minutes to answer it completely. 30 is a problem of moderate difficulty and or complexity. This one may involve more than 2 hours work to solve satisfactorily, or even more if the TV is on. 40 is quite a difficult or lengthy problem that would be suitable for a term project or in classroom situations. A student should be able to solve the problem in a reasonable amount of time, but the solution is not trivial. 50. A research problem that has not yet been solved satisfactorily as far as the author knew at the time of writing, although many people have tried. If you have found an answer to such a problem, you ought to write it up for publication. Furthermore, the author of this book would appreciate hearing about the solution as soon as possible, provided that it is correct. By interpolation in this logarithmic scale, the significance of other rating numbers becomes clear. For example, a rating of 17 would indicate an exercise that is a bit simpler than average. Problems with a rating of 50 that are subsequently solved by some reader may appear with a 40 rating in later editions of the book and in the errata posted on the internet. See page 4 or page IV. The remainder of the rating number divided by 5 indicates the amount of detailed work required. Thus, an exercise rated 24 may take longer to solve than an exercise that is rated 25, but the latter will require more creativity. All exercises with a rating of 46 or more are open problems for future research, rated according to the number of different attacks that they've resisted so far. The author has tried earnestly to assign accurate rating numbers, but it is difficult for the person who makes up a problem to know just how formidable it will be for somebody else to find a solution, and everyone has more aptitude for certain types of problems than for others. It is hoped that the rating numbers represent a good guess at the level of difficulty, but they should be taken as general guidelines, not as absolute indicators. This book has been written for readers with varying degrees of mathematical training and sophistication. As a result, some of the exercises are intended only for the use of more mathematically inclined readers. The rating is preceded by an M if the exercise involves mathematical concepts or motivation to a greater extent than necessary for someone who is primarily interested only in programming the algorithms themselves. An exercise is marked with the letters HM if its solution necessarily involves a knowledge of calculus or other higher mathematics not developed in the book. An HM designation does not necessarily imply difficulty. Some exercises are preceded by an arrowhead. This designates problems that are especially instructive and especially recommended. Of course, no reader or student is expected to work all the exercises, so those that seem to be the most valuable have been singled out. This distinction, however, is not meant to detract from the other exercises. Each reader should at least make an attempt to solve all the problems whose rating is 10 or less, and the arrows may help indicate which of the problems with a higher rating should be given priority. Solutions to most of the exercises appear in the answer section. Please use them wisely. Do not turn to the answer until you have made a genuine effort to solve the problem by yourself, or unless you absolutely do not have time to work this particular problem. After getting your own solution or giving the problem a decent try, you may find the answer instructive and helpful. The solution given will often be quite short, and it will sketch the details under the assumption that you have earnestly tried to solve it by your own means first. Sometimes the solution gives less information than was asked. Often it gives more. It is quite possible that you may have a better answer than the one published here, or you may have found an error in the published solution. In such a case, the author will be pleased to know the details. Later printings of this book will give improved solutions, together with the solver's name where appropriate. When working an exercise, you may generally use the answers to previous exercises unless specifically forbidden from doing so. The rating numbers have been assigned with this in mind, thus it is possible for exercise n+1 to have a lower rating than exercise n, even though it includes the result of exercise n as a special case. And we have a summary here. And then we have our first set of exercises, which is pretty funny. So the first one, what does the rating M20 mean? Well, it means that it's for mathematically oriented learners, and it is, let's say, should take about a quarter an hour for such a person. Number two, of what value can the exercises in a textbook be to the reader? Well, it can help them put the knowledge into practice. It can help enhance retention. It can surface, I would say, like not necessarily misunderstanding, but non-understanding. Because I used to tell my students back when I had students for longer than an hour or so at a time, and they never found this at all convincing, by the way, that exercises that you could not do were actually the best. Those should be your favorite exercises. Those should be the ones that you treasure the most, and you should be the least willing to look at the solutions for, because that is proof to you that you are missing some learning, and you have then a perfect assessment for yourself. If you learn something and then you can later do that task, then you have certainly learned something important. If you still can't do it, then your learning is still not taken to the required point. So you've got, rather than, many people kind of feel that they've understood something or feel that they haven't understood something, the exercises can tell them whether they've understood it or not, which I think is very valuable, because it can be hard to know whether you've understood something sufficiently. It will not surprise anyone to know that people did not really find this very convincing, although it is still true. Question 3. Prove that 13 cubed is 2,197 and generalize your answer. This is an example of a horrible kind of problem that the author has tried to avoid. So I did actually, I will admit, I looked up the solution to this one, because it told me something about my own lack of understanding and what I would need to know in order to do this work. So to me, wow, it's let me just zoom in on this a bit. To me, like I've not done a lot of mathematics since high school, secondary school, and secondary school in the UK does not cover proofs, or it doesn't really cover calculus. Honestly, I think it covered a bit of calculus for me, and so I know a little bit, but not loads. So for me, I mean, proving this is putting it into the calculator and getting the right answer out. 2197. However, there were two issues with this. The first issue, of course, is that I learned that my MacBook has a technology in it in which it completes the answers to equate to things like this. And so I just need to press the equals button and it will fill out the answer. So I had to work out how to disable that. Turns out you cannot disable it in Safari at all. You used to be able to, but you can't anymore. So I had to switch to Chrome. So there you go. That's the first problem. The second problem is, obviously, I'm missing something about what a proof is. And so I will need to spend some time with proofs, and we will be spending some time with the book of proofs soon, probably quite soon, so I can understand what I'm missing there. I did look up the answer, though, to try to work out what form the answer looks like. And I believe what you are supposed to do is to apply some rules. And I think the rules are something like, it's something like this. Yeah, it's something like this. Or something. Anyway, I need to get a better diagramming tool. I will get a better diagramming tool at some point. There we go. Oof, it's rough, isn't it? Yeah, so it's something like this. You apply this, and I think I saw this person reduce it down to like something like something like this, and then reduce it down another step, of course, to 13. This one more time. I need to make this even smaller, actually. No, there we go. And then you've got, I guess, the rules of, you got some sort of, somehow you can use multiplication, though you can't use powers or something like that. And so you get this. And then somehow that's allowed. 2197. Or something. I'm sure that I will look back on this video and be like, you idiot, you don't know anything. But that's as far as my understanding goes there. We're going to get through the first chapter, the first proper chapter and work out what mathematical knowledge we will need to learn before we start diving into other textbooks. But this will give you some idea as to where I am coming from in my mathematical maturity at this point. And then the fourth exercise made me laugh a lot because I was like, I read it, I was like, okay, well, I'm definitely not going to do that. And I was like, wait a minute. Haven't I seen this problem somewhere before? And I had, because this is Fermat's last theorem, and famously at the time of initial publication, unproven theorem, I guess. And I was like, maybe it's like a funny version of it that you can solve easier, but it's not. I think it's the actual theorem. And I was like, 45. So I guess, 45 would indicate, because anything above 45 is unsolved. It's an open problem. So I went back and looked at the earlier editions, and in the first and second editions, this is HM50, so unsolved. I guess this is supposed to, if you think you're going through this and thinking, I'm going to do all the exercises, I think this will, that's supposed to be like, no, you're not. You're not going to do all the exercises because, you're not going to do this one. But then somebody did solve it, so he had to change it in the third edition to 45. Now, understanding that proof is a whole career in itself, I should think. But yeah, made me laugh to see this in here. All right, how's chat doing? Oh, we've had some good chat here. People like flowcharts. Gioma, I'm reading The Art of Computer Programming by Donald Knuth. Oh, the French says the best authors talk too much. Oh, cool, thank you. Okay, difficulty goes up exponentially. Thank you. Yeah. Yeah, there are answers at the back. So Atom Fighter knows about the maths. For the generalize your answer part, you need to apply mathematical induction. It's a recurrence relation. Interesting. Interesting. Yan Shufim taught maths at university for 15 years, and this is one of the hardest, most abstract things to get your head around. Yeah, point of the books is to level up. Yeah, that's right. Not taught at school. Yeah, they are. I should think they are jokes. Jokes for mathematicians. Andrew Wiles won the Fields Medal. Yeah, I spent some time looking at little videos of him talking about because he went on this he spent, there was this whole story about him. He met his future wife. Sorry, stop looking away from the microphone. He met his future wife, and hello, V470N. Hello. He met his future wife, and he'd been working on Fermat's last theorem for a long while, and it had sort of taken over his life. He was teaching during the day, researching during the day, and then coming home and working on his proof of the theorem. And then he met his future wife, and I think he told her I think it might have even been it was on their honeymoon. So he'd married this woman, and they'd gone on their honeymoon, and he was like, by the way, I spend all of my time working on a proof to Fermat's last theorem. And I guess by that point she's locked in enough that he's not worried that she's going to leave him over it. And she doesn't, I believe. And then he comes up with a proof, and then he announces it, and he publishes it, and then I think he doesn't publish it actually. He gives a talk to a bunch of people in the field who can understand this, and then somebody does the biggest not more of a comment than a question in history, and basically points out like a, probably through a question, like a flaw in his proof. And so he's like, oh no, obviously, because, he thought he had it. But like he basically, he himself is then in the long line of people who have almost proven Fermat's last theorem, but not quite. Or have thought they had a proof but didn't have a proof. And then he spends, I think, a year just trying to work through his proof to see if it can be fixed, and he decides it can't be fixed. And he decides, I think he's like a couple of days away from publishing his work, which results in no proof for Fermat's last theorem, so that at least others can benefit from it. And so he's trying to work through his work, and he's trying to come up with a good way to explain why it doesn't work. And then he like looks at it and he's like, oh wait, the reason it doesn't work, like the technique I can't use here or couldn't use earlier on, actually suddenly now applies. And he like sees the solution, and he goes down and says to his wife, he's like, I think I've got it. And she thinks he's like talking about some like toy that they've lost or something. And then he's like, no, I think I've got the proof. Yeah, just an amazing life to have lived through. I think if they had like the Rick and Morty like life simulator, it would be amazing to live through that man's life, just to experience what that moment must have been like. Also, his office is a complete mess, which is kind of reassuring about my office. But very moving story, really. Yeah. I wonder what he's doing now. Anyway, we can face our problem. We can arrange such facts as we have with order and method. Hercule Poirot in Murder on the Orient Express. So he's fairly widely read, I think, as you would imagine. Let's look at the contents. So we've got the procedure for reading the set of books, etc., exercises. And we've got the basic concepts, which includes some mathematical preliminaries. We're going to talk about induction, I guess. Numbers, sums, products, integer functions, permutations. I know a little bit about permutations. I studied about half of Chris Peake's Stanford probability for computer programmers course. Nice course. Nice. I like the guy's work, actually. But I only went halfway through. But the first half is a lot about permutations. Binomial coefficients. I always forget the formula there, but I know a little bit about harmonic numbers, nothing. Fibonacci numbers, I know what it is. Generating functions, not sure. Analysis of an algorithm. Asymptotic representations, that'll be O notation. Mix. Fundamental programming techniques. Subroutines, coroutines. Interpretive routines. Input and output. History and bibliography. Lists. Trees. So what do we go into? Lists. Lists will be interesting. Fine. Trees. I suspect I will find the maths the hardest part. I should hope I will, but we'll find out. And then some appendices. And this nice tree here, which you can click. What happens when you click it? Nothing. Okay, I just made that up. Okay. The problems that Knuth solved are what we call compiler theory today. He's one of the founding fathers. That's true, yeah. It's kind of interesting, Knuth stuff about compilers, because like he did a lot of research into languages and like parsing and that sort of stuff. But last I spent time with it, a lot of it is not used. Like in everyday programming languages, a lot of it still uses a lot of it doesn't use the more advanced features of his work. It uses recursive descent instead, which is kind of interesting. So it'd be interesting to know when we get there, if we get there, what the the current big like Zig, for example, I think uses recursive descent. I think most languages still use recursive descent, which is like a kind of primitive version. Can't wait to get to chapter 2. Find programming by far the hardest part. Well, maybe I will as well. I'm kind of excited to get to chapter 2 because I'm going to build a simulator of some kind, and the simulator should be, hopefully it won't be like a LaTeX style 10-year diversion, but I think there could be something good to build there, which will make the streams a bit more engaging, let's say. Yes. Okay. What are we going to do? What time are we on? 1:15. Let's work through a bit more. I don't want to take exactly as long as Knuth took to write it. So we should be able to work through. I think we should be able to get to the first set of exercises, and then I'm going to read through these exercises and I'm going to see which I can actually do with my current level of mathematical understanding, and then we'll probably go back. I'll probably end the stream there, and then I will probably do a bit of deciding what books I'm going to use to research the prerequisites, and then the next stream will be mostly on that. So let's see. Oh, okay, it's pretty long actually, now I think of it. Okay. Chapter 1, Basic Concepts. We're not supposed to read the quotes, but I'm going to read them anyway. I don't know why he said don't read them. Like, is he embarrassed about them? Maybe he's doing it so that we, like, it's like reverse psychology. He wants us to read them. Practice yourself, for heaven's sake, in little things, and thence proceed to greater. By my lack of Latin is going to show here. Epictetus Discourses, AD 110. I believe one of the things he does is he includes quite a lot of history in these, and I love like the history part of computing, like the fact for example, one of my favorite things that I like, there's so much you could research, but one thing that I desperately want to spend some time researching at some point is the person who invented first studied, let's say, or at least was one of the pioneering people in binary numbers, Leibniz. He believed that they were mystical. He believed that they had a kind of spiritual resonance, that he was a Catholic, but he was kind of interested in, like, I guess what he would describe as like Eastern philosophy or something, and the I Ching. I believe that's how you pronounce that. No, I'm not really sure, but let's say. And binary numbers come out of his study of the I Ching, or like heavily tied up with it. So like, what is he talking about? Like, I desperately want to spend some time on that. So I, probably won't be in here, but there's so much interesting history in here. And Knuth also, now I think of it, this would make a fascinating pair of videos. So Leibniz, he had this thought about binary numbers and their spiritual significance. And Knuth wrote a book, I think it's titled Things Programmers Rarely Talk About, or something like that. And a lot of it is about the Bible. He kind of does almost like a Gnosticism like thing, I think. That's probably out of turn to say. I don't know that much about what he wrote, but again, spirituality and computing for him, he combined those things. I wonder, I'm definitely going to stir those things together at some point, because I'm so fascinated as to what they're going to talk about in those passages. Anyway, many persons who are not conversant with mathematical studies imagine that because of the business of Babbage's analytical engine is to give its result in numerical notation, The nature of its processes must consequently be arithmetical and numerical rather than algebraical and analytical. This is an error. The engine can arrange and combine its numerical quantities exactly as if they were letters or any other general symbols, and in fact might bring out its results in algebraical notation were provisions made accordingly. So that's from Augusta Ada, Countess of Lovelace, 1843. Guess that will be the same famous Ada Lovelace. I didn't realise she was a Countess of Lovelace, and her name was Augusta. Maybe was that first name? Maybe. Ada's more of a first name now. Maybe that's anyway. Something to research. I will come back to that. Okay, algorithms. The notion of an algorithm is basic to all of computer programming, so we should begin with a careful analysis of this concept. The word algorithm itself is quite interesting. At first glance, it may look as though someone intended to write a logarithm, but jumbled up the first 4 letters. The word did not appear in Webster's New World Dictionary as late as 1957. Wow, really? Huh. The word algorithm did not appear in Webster's dictionary as late as 1957. We only find the older form algorithm, with its ancient meaning, the process of doing arithmetic using Arabic numerals. During the Middle Ages, abacists... give me 1 second, I'll be back shortly. Abacists. I'm going to keep that there in case I need to use it for the exercises. Abacists computed on the abacus and algorists computed by algorithm. Huh. Now that is really something, isn't it? During the Middle Ages, abacists computed on the abacus and algorists computed by algorithm. So this is the distinction between performing calculations which, this is the distinction, I suppose, between maybe this and like calculating this, maybe. Could be. Do we think? Is that what is meant by that? Why am I Excalibur saying so terrible? Oops, okay. Yeah, is he saying that there was this distinction between abacists might calculate this on an abacus, which if I knew enough about this abacus, I could probably do. I do know a little about it. It's this is a Chinese one, so there are different abacuses, let's say, in different parts of the world, and they have different means for using them. And this one, I think actually, let me do it in reverse so it's easy for you to see. This one, I think this is 1, 2, 3, yeah, and then 4. So four up. This would be easier if it was on the floor, obviously. And then I think these start up here, and then you move this down. This would be 5. This is quite hard to do standing up. This would be 5. No, wait, this would be 5. Then this is 6, 7. Oh gosh, I've messed it up. 7. No, wait, this is 8 now. I don't have enough fingers to do 9, but just imagine that one at the bottom has gone up. Let me do this. This is 9. And then this would be 10. And I think there are algorithms, well, abacisms, I guess, that let you perform calculations. Like there are routines for which you can use to add and multiply with these, which involve using these top and bottom ones, which are not used to represent numbers, I think. But it turns out that this way of using the Sonpo, is it? What's the name of the Chinese abacus again? Let me look that up. Swanpan. The routines for using the Swanpan, I think, are part of they're like a UN intangible heritage. And they used to teach them much more, but then calculators came along and they don't teach them so much anymore, which is kind of interesting. Anyway, showing off what I know about abacuses. Atom Fight reading about Leibniz. Yeah, cool. Go Noob 42. Is this a book club? Can I join? Sure. I mean, I guess it is a book club in a way. Yeah, I wish it was a cat break. It's an abacus break only. Yeah. So anyway, abacus. So maybe this is I'm probably butchering the distinction between. Well, it's not updated there. No, it has. The distinction between. There's a distinction here between abacists and algorists. I suppose abacists would be computing physically using these, and algorists would be using. Maybe the distinction is really one of using an abacus to compute versus using sums on paper with numbers, with like Arabic numerals. I suppose that's probably what we're talking about. But there is I suppose, yeah, anyway, let's continue reading. By the time of the Renaissance, the origin of this word was in doubt, and early linguists attempted to guess at its derivation by making combinations like algiros, painful, and arithmos, number. Others said no, the word comes from King Algor of Castile. Finally, historians of mathematics found the true origin of the word algorithm. It comes from the name of a famous Persian textbook author, Abu Abd Allah Muhammad ibn Musa al-Khwarizmi, literally father of Abdullah Muhammad, son of Moses, native of Khwarizm. I think that's right. The Aral Sea in Central Asia was once known as Lake Khwarizm, and the Khwarizm region is located in the Amu River basin just south of that sea. Al-Khwarizmi wrote that the celebrated Arabic text Kitab al-Jabr wal Mukabala, Rules of Restoring and Equating. Another word, algebra, stems from the title of that book. Oh, yes, of course. Algebra, which was a systematic study of the solution of linear and quadratic equations. For notes on Al-Khwarizmi's life and work, see H. Samanek Lecture Notes in Computer Science 122. I may do that. That would be so interesting, actually. I might make a little note. Can I highlight? Can I highlight? Awful. Really, really dire. Okay, what about... No, that's terrible. Come on, let's get something going. Can we do any sort of decent highlighting that is not horrible? Whatever. Gradually, the form and meaning of algorithm became corrupted, as explained by the Oxford English Dictionary. The word passed through many pseudo-etymological perversions, including a recent algorithm in which it is learnedly confused. Oh, wait. It's a quote. Gradually, the form and meaning of algorithm became corrupted, as explained by the Oxford English Dictionary. The word passed through many pseudo-etymological perversions, including a recent algorithm in which it is learnedly confused. So I guess algorithm is they're saying it's sort of silly to use that word. With the Greek root of the word arithmetic. Right, I see. So it was confused with arithmetic. That's where the th came from, because it would be like arithmetic. This change from algorithm to algorithm is not hard to understand in view of the fact that people had forgotten the original derivation of the word. An early German mathematical dictionary, Wohlstandiges Mathematisches Lexikon, from Leipzig 1747, gave the following definition for the word algorithmus. Under this designation are combined the notions of the 4 types of arithmetic calculations, namely addition, multiplication, subtraction, and division. The Latin phrase algorithmus infinitesimalis was at that time used to denote ways of calculation with infinitely small quantities, as invented by Leibniz. By 1950, the word algorithm was most frequently associated with Euclid's algorithm, a process for finding the greatest common divisor of 2 numbers that appears in Euclid's Elements, Book 7, Propositions 1 and 2. There was a great 3 blue, 1 brown, not him, but he posted, when he does that sort of summary of, he did that time when a bunch of other people posted videos on his channel. There's a great one about Euclid's Elements in there. Would recommend as a non-mathematician. Although, to be fair, by the end of working through this book, I will have to be a mathematician in some sense. It will be instructive to exhibit Euclid's algorithm here. Algorithm E, Euclid's algorithm. Given 2 positive integers m and n, I think I've implemented this actually. Find their greatest common divisor, that is, the largest positive integer that evenly divides both m and n. All right, let me just get that clear in my mind. Because there is a risk that I will just skim this. Let me actually just go, okay. So let's say we've got, can you still see this? Yes. Sorry, do some window management. Okay. Given 2 positive integers m and n, find their greatest common divisor, which I know this is like simple stuff. I just always get confused by this particular thing. That is the largest positive integer that evenly divides both m and n. So let's say if we have classic 12, and let's go 24. What we're looking for is the largest positive integer that evenly divides both m and n. So, for example, 2 would divide both, but there's a bigger one. So 2's not right. Would 3 divide 24 by 3? So we got 3. Is there a bigger one? 12 over 4 is, so 4 would be that. 5 wouldn't go. 6 would go. Does 8 go into 24? Doesn't go into 12 though. And then 7 definitely doesn't. So I suppose it would be 6. Let me just check this. Greatest common divisor calculator of, yes, I will agree to the cookies. 12, oh my gosh, I accidentally clicked on an IQ test. Okay, 12, I guess it's 12. I guess it's 12. I guess it can be the same number. Okay, fine. Largest positive integer that evenly divides both m and n. So we're looking for something, I think, like that. I think that's what we're talking about. Please highlight these two Wow, so annoying. Yeah, okay. So the algorithm works like this. And I guess we can use this algorithm now. Oh my gosh, please do not waste my time by having such small x height. Divide. Okay, so let's do this. Can you see this? Yes, you can. Okay, divide m by n. So we divide 12 by 24. And we let r be the remainder. So in which case, the remainder of 12 by 24 is 12, right? Wow, terrible. Yeah, because 12 doesn't go into 24 at all, so its remainder is going to be 12. If r is 0, the algorithm terminates. N is the answer. So, and then E3, set m to n and n to r, and then go back to step E1. Okay, so I guess we're starting off with m equals 12 and n equals 24. So at this point we set m to 24 and n to 12. We go back to E1. Wow, okay, my head's in front of this. Okay, let me zoom out a bit. There we go. Okay, hopefully that should be good. Okay, yeah, E1, divide m by n. So 24 divided by 12. The remainder of doing so will be 0, because 24 over 12 is 2 exactly, so there's no remainder. E2 is yes, and n is the answer, and n is 12. So yeah, it's exactly what the exactly what the calculator told us. Okay, cool. So that's an algorithm. Yeah, 12. Yeah. Yeah. It definitely seems like having the bigger number be m to start off with saves a step. Okay. Of course, Euclid did not present his algorithm in just this manner. The format above illustrates the style in which all of the algorithms throughout this book will be presented. Okay. Each algorithm. So I guess we've got this format. This format. In this format, we've got a kind of. Oh no, I'm highlighting again. Let me turn off this highlighting. This format, we have like a summary, the procedure, and this step number. Okay, fine. Each algorithm we consider has been given an identifying letter, E in the preceding example, and the steps of the algorithms are identified by this letter followed by a number. The chapters are divided into numbered sections. Within a section, the algorithms are designated by letter only, but when the algorithms are referred to in other sections, the appropriate number is attached. For example, we are now in section 1.1. Within this section, Euclid's algorithm is called algorithm E, while in later sections it is referred to as algorithm 1.1e. And it's linked here, which is pretty handy for us. Each step of an algorithm, such as step E1 above, begins with a phrase in brackets that sums up, I already did this, that sums up as briefly as possible the principal content of that step. The phrase often appears also in an accompanying flowchart such as Fig 1, so the reader will be able to picture the algorithm more readily. After the summarizing phrase comes a description in words and symbols of some action to be performed or some decision to be made. Parenthesized comments, like the second sentence in step E1, may also appear. Comments are included as explanatory information about that step, often indicating certain invariant characteristics of the variables or current goals. They do not specify actions that belong to the algorithm, but are meant only for the reader's benefit as possible aids to comprehension. Find remainder. Is it 0? Reduce. Okay, fine. So a little more concise, let's say. Interesting use of the word reduce there. I suppose that must have some meaning in mathematics. Beyond, I mean, it has meaning in programming as well, but it's one of those words people use for folding. I tend to prefer reduce because I'm more used to it, I suppose. But maybe it relates to something in maths. Reduce n modular m. Oh, does it just mean... is that all it means? Just the mod operator, as I would call it. Interesting. So I wonder why the reduction... I guess because there's a reduction method, for example, in JavaScript on lists, which to me, I always use the analogy of like a cooking recipe. Like you reduce a sauce to its principal, to its concentrated form. But maybe it emerges from modulo as well, because it doesn't mean modulo exactly in when iterating. Anyway, the arrow in step 3 is the all-important replacement operation, sometimes called assignment or substitution. He uses the left arrow. Oh my gosh! So I have such beef with people using, with the fact that programming languages use equals for assignment, when really it doesn't. Like, it's sort of odd that it uses equals for assignment. Really, makes far more sense to use the left arrow as the R language does, but almost no languages use the left arrow. I guess because it's 2 characters, and here Knuth is hopefully agreeing with me. Anyway, let's read on and find out if he does before I go too far on that. Sometimes called assignment or substitution. M left arrow n means the value of the variable m is to be replaced by the current value of variable n. When algorithm E begins, the values of m and n are originally given numbers, but when it ends, the variables will have in general different values. An arrow is used to distinguish the replacement operation from the equality relation. We will not say set m equal to n, but we will perhaps ask, does m equal n? The equal sign denotes a condition that can be tested. Terminal Zyro, thank you so much. I think it's Zyro. Let me know if I'm pronouncing that correctly. Thank you so much. Where was I? Set m equal to n, but perhaps ask, does m equal n? The equal sign denotes a condition that can be tested. The left arrow sign denotes an action that can be performed. The operation of increasing n by 1 is denoted by n left arrow n plus 1. Read n is replaced by n plus 1, or n gets n plus 1. Gets. Interesting. In general, variable left arrow formula means that the formula is to be computed using the present values of any variables appearing within it. Then the result should replace the value of the previous variable at the left of the arrow. Persons untrained in computer work sometimes have a tendency to say n becomes n plus 1 and to write n right arrow n plus 1 for the operation increasing n by 1. This symbolism can only lead to confusion because of its conflict with standard conventions and should be avoided. I was in the process. I later did not make this video, but I was in the process of making a video about a pet topic of mine, which is the analogy used to teach variables to beginning programmers. And the common analogy that is used is the box analogy. And the analogy goes like, you have like a variable as a box, and it has its name, which is its label on the top, and then you have a number that you put inside it, or a value you put inside it, and you can look into it and pull it out or whatever. The only problem with that analogy is that it makes no sense with how variables actually operate, in my opinion. And like you end up with this like weird analogy, which makes sense at first in that it gets the student to stop asking you questions. But let's say we have 45 as a number here. And we have our box, which we'll call box, let's say A. And then let's put it in here. And let's say, so this represents like the line of code A equals 45. In programming terms, is all this would be in JavaScript, for example. Now, what happens if you later say A equals 46? Well, you've got your other number here, and well, you put it in here. Okay, so fine. You probably maybe it replaces this, or we got to pull this out. Let's go somewhere else. I don't know. And then if you have two variables, like B here, and let's say we have A equals 45 and B equals 46, and then A equals B. Let's say this is our code, and we put this would create this. Sorry, this would create this situation. We've got this here. Then this line here, A equals B. If you've introduced the analogy of the box to describe variables, you've then got like a weird situation where, okay, so what actually does happen here? Like this, maybe we can say this ends up being 46, but a lot of beginners don't even intuit that at the start. So the question, I guess, is like at the end of this program, what is A and what is B at the end of this program? And the correct answer is both are 46. But the box analogy doesn't really help you very much here, because you sort of think, well, where does the 45 go? Does B go inside A in some way? Like, does the whole B go inside A, like the 45 did before, and so are they now linked in some way? Or is something else going on? Like maybe they swap over, and I've taught this to total beginners, and the variety of ways that they understand variables is quite astounding. So I often go through this through this exact code to get to grips with it. Anyway, I had this whole notion that, and there's probably I'm going to say I think this is a good idea, but I haven't worked out how to make it work in practice yet. That actually we should, like, another way of teaching variables is more like the abacus. The abacus exists like a cell of memory in that it can be configured in a certain way. So let's say this is like, it's not actually, but let's say this represents 3, and we have another abacus that's like set to like 2 or something. Then the act of setting a variable is looking at one abacus, so let's say the B abacus, and setting A to be exactly the position that B is in. So that's what setting a variable is. And they're not linked, they're just, you're copying over the arrangement of one to the other, which is basically also quite close, though not exactly the same as, how memory actually works, in that memory is working as a configuration of physical matter. It's not a box with a thing in. It is a configuration of physical matter in such a way that it can represent a number. And when we are doing A plus B, we are copying whatever the arrangement of B is, and we're making A look exactly like what B looks like. So we're copying over the arrangement of B into the arrangement of A. This, I think, is a better foundation for building and understanding a computer based on. Anyway, I didn't make that video, but I did buy the abacus, which is why I have the abacus, and it is kind of a pretty abacus, I think. So I got that out of it. Yeah, L values and R values I'm not familiar with, but yeah, that's my answer, I guess. I think that the cell model of memory is quite important for beginners, and so I think relatively quickly after beginners start to just play around with programming and have fun with it, we should introduce the idea of like a cell of memory as holding a value through arrangement. And if you can build on that idea as that's the underlying idea of the way the computer works, that it's made up of many, many cells, each of which can be arranged in a certain way, and that variable assignment is about assigning particular arrangement to a particular cell, we have a better foundation for building off of and a better intuition. But yeah, indeed. Yeah, so Jan Shufan says, I found out very recently that Python does something weird here. It will sometimes quietly set A and B to point to the same area of memory if they have the same value. And I still haven't worked out when or why. Yeah, so yeah, it's, yeah, without seeing the code, I couldn't comment exactly, but you could be referring to, yeah, there's something about, so this often happens with strings, but I think it also does happen with numbers. Yeah, I think the first 256 numbers are like instantiated at particular locations in memory for a Python program, and they are static, so they will never change, but variables get pointed to particular areas. One of the difficult things about teaching with high-level programming languages is you can't really rely on these facts to make sense to a beginner, unfortunately. But yeah, it is. I think oh no, that's Java actually. I think Java does that. Python maybe does it too. Could students already be accustomed to the idea of copy and paste on a computer? Might be useful as part of the explanation. It's true. Yeah, it's true. I think a lot of what the chat. So there's many ways to help beginners get enough of a sense to build small computer programs. The difficult part is to then take them from an intuition which helps them get by to something which is close enough to the truth of how this thing works that they then have an understanding they can build on long term. And so their intuition will be well tuned towards learning more advanced topics. So, for example, like if you have, so for example, here's another example that Dan Abramov did this course called Just JavaScript. And he had his own notion of what the right way to understand variables and memory in JavaScript was. And it was purely through reference. So the notion was that he wanted to give students was all of the data that you're operating on exists in a kind of imaginary space, and your variables they have, I think he actually called them hooks at the time. Your variables have hooks into like these values that exist in this imaginary space of memory, which is not cellified. It's just like you have like there's a 1 over here and like the string Fred over here and like an object over here, and your variables have these kind of chains which tie them to those sort of unnamed objects in space. And so you would build up this understanding that what I think of as fairly close to the binding understanding of variables, that variables are fundamentally names, and the names get pointed to actual pieces of data. And so you should build a distinction between the idea of a binding and an actual piece of data, which is also a kind of interesting idea, and is a big part of how variables operate. And one of the reasons that variables are such an interesting topic for beginners, because there are so many different things about such a simple concept. But my issue with this notion that he had to teach variables this way to beginners was that it doesn't. You have to build quite a lot around this idea. Like this idea is quite interesting for JavaScript, and it's quite interesting if your task also is to try to make React hooks make sense to beginners, because React hooks they're called hooks for one, and they work pretty much exactly like this. You have a name, and it also gives you a reference to some thing in memory which is managed by somebody else, and you shouldn't be thinking about how it's stored or arranged. That's done for you, which it's kind of an interesting idea, but it's quite then hard to transfer that idea outside of the realm that it's designed for. You have to kind of, if that was your one idea that you had about variables, if you wanted to go and learn C, you would need to like change your ideas of variables quite a lot. And so suddenly in your process of teaching someone the beginnings of programming, you've built in a big barrier in front of them to learn another part of programming. So what I'm often trying to think about is, what are the foundational ideas that we can teach people in ideally any programming language? Foundational, let's say, analogies or mental models, let's say. Don't love that word, but let's say, ideas, schema, concepts. What are the concepts that reduce the barriers towards future learning in adjacent spheres? And often this looks like, what are the ideas about, for example, variables that are simple enough that they can be understood by a beginner, but accurate enough to the underlying reality that it's going to apply also, and going to be easy to build on to understand, like variables in JavaScript and variables in Python and variables in Java and variables in C and variables in even COBOL, such that you can then look at it and be like, oh, it's like that, but they've built something additional on it. And so with variables, if you could start off with the notion that variables like are a named cell with a particular value in them at a particular time, and setting variables looks like arranging that in a particular way, you could then layer on the idea that also variables can exist as a sort of reference, as a pointer to something else. And then maybe if you can build on that, you can then understand all of how JavaScript and Python works, and how maybe Python is going to use this idea of references in order to get two variables to reference the same piece of memory, or they might reference different pieces of memory. Maybe, but I'm not 100% convinced by any of the ideas I've had so far on that. And also people aren't really finding it that difficult to learn about variables, so it's kind of a theoretical problem anyway, but an interesting one that my mind goes back to. And maybe, I don't know, maybe the world of learning programming is going to change quite a lot, because it used to be that you had to learn to code to be a software engineer, and that's still quite true, but it's much less true now than it was a decade ago, because AI can save you / rob you from a lot of your programming practice time. And I wonder what that will do for what people need to learn. Anyway, big tangent. Where were we? Oh yeah, so all of this is coming from the left arrow. The left arrow I like because it's directional. It doesn't get confused with like equality. It doesn't get confused with like high school algebra, where you've got the equals, meaning, always equal. I had some learners who sometimes, if you show them like A equals B and A and B are different values, they assume it should be an error. So this syntax does not fall into that problem. Anyway, okay, so we were here. Will we get through this? We'll probably try and get through this chapter today. Notice that the order of actions in step 3 is important. Set M to N and N to R is quite different from set N to R and M to N, since the latter would imply that the previous value of N is lost before it can be used to set M. Thus, the latter sequence is equivalent to set N to R, M to R. Is this the same? Oh no, it's not. Okay, I think it's fine. When several variables are all to be set equal to the same quantity, we can use multiple arrows. For example, set N to R, M to R, may be written N to M to R. To interchange the values of two variables, we can write exchange M and N. This action could also be specified using a new variable t and writing set t to M, M to N, and N to t. An algorithm starts at the lowest numbered step, usually step 1, and it performs subsequent steps in sequential order unless otherwise specified. In step E3, the imperative go back to step E1 specifies the computational order in an obvious fashion. In step E2, the action is prefaced by the condition if r equals 0. So if r is not equal to 0, the rest of that sentence does not apply and no action is specified. We might have added the redundant sentence, if r is not equal to 0, go on to step E3. The heavy vertical line, oh yeah, I was wondering about that, appearing at the end of step E3 is used to indicate the end of an algorithm and the resumption of text. I guess like magazines, they have that, what's the name of that? There's like a character they have. It's like a pillbox or something. Tombstone. It's called the tombstone. So I guess that's a tombstone. Decameron, hello. Knowing how stuff works under the hood, even if from a bird's eye view, is always welcome, but sometimes in real life scenarios, working with a high-level language such as Python that does all the abstraction for you is more than enough. I'm not promoting ignorance, mind, but realism. Use the right tool for the right job. If you want to expand your knowledge in your spare time, then that's a great plus for you. Yeah, makes sense. Yeah, I mean, there's always a trade-off towards how, and it can be delightful, really, not knowing sometimes. Like it can be, you can both having a depth level understanding and a surface level intuition without depth can enable you to make delightful leaps in actual practice, I think, and also not spend your whole life just digging into the details of things that are not required. I used to be a very fast worker when I was a software developer in my early 20s. And I worked, we did pair programming at this company, and I worked with a guy who, he was very slow. And he was very slow because he wanted to understand all of the details of what we're going to do. All of the edge cases, he thought of them, and he wanted to go into all of them. And I found it so frustrating. I found it so irritating, very difficult. And I was not as mature as I am now, and I'm not that mature now, but I particularly wasn't mature then. And I would get, I think in my recollection, I didn't cross the line, but I was too irritated at him. I was too visibly irritated at him. But the thing that I eventually realized is I definitely got a lot more done, but my work would often need to be not redone exactly, but I would often need to go back to it and be like, oh, I missed that case or something like that. But I don't think I ever encountered a single bug in anything he did. Like there was never anything he missed. It did take him a long time to get there, and that was a business concern at some points, but his work essentially never had any bugs in that at least that were discovered while I was there. So maybe us working together was maybe we made a good team, and I should have been much nicer to him than I was. I still regret that. Yeah. Anyway, that's where maturity comes from, I guess, experience. We have now discussed virtually all the notational conventions used in the algorithms of this book, except for a notation used to denote subscripted or indexed items that are elements of an ordered array. Suppose we have n quantities, v1, v2, through to vn. Instead of writing vj for the jth element, the notation v square brackets j is often used. Similarly, a I, j is sometimes used in preference to a doubly subscripted notion like aij. Okay, so we're not going to be totally in the maths verse, fortunately. There's a bit of programming here. Sometimes multiple letter names are used for the variables, usually set in capital letters. Thus, temp might be the name of a variable used for temporarily holding a computed value. Prime k might denote the kth prime number, and so on. So much for the form of algorithms. Now let us perform one. I bet he enjoyed writing that. It should be mentioned immediately that the reader should not expect to read an algorithm as if it were part of a novel. Such an attempt would make it pretty difficult to understand what is going on. An algorithm must be seen to be believed, and the best way to learn what an algorithm is all about is to try it. The reader should always take pencil and paper and work through an example of each algorithm immediately upon encountering it in the text. I suppose I did that. I'm such a good student. Usually the outline of a worked example will be given, or else the reader can easily conjure one up. This is a simple and painless way to gain an understanding of a given algorithm, and all the other approaches are generally unsuccessful. Let us therefore work out an example of algorithm E. Suppose that we are given M is 119 and N is 544. We are ready to begin at step E1. The reader should now follow the algorithm as we give a play-by-play account. Okay, let's do it. All right. Where's my... Here we go. So, you know what he's done? He's made he has made M smaller. He's made M smaller than N. Perfect. Okay, so we start off with this. Let me just make sure I'm still showing you the right thing. Great. Let me move this across. Okay. Given M119 and N544, okay, fine. Dividing N by N in this case is quite simple, almost too simple since the quotient is 0 and the remainder is 119. Okay. So let's do that then, I guess. M by N is quotient is 0, 119. They usually put I think I was taught in school to do this, put numbers on the start or something. Okay, so yeah, so then R is set to 119. We then proceed to step E2, and since R is not equal to 0, whoa, okay, terrible. Yeah, so this is, yeah, this will be E2. I guess I should do E2, shouldn't I? I should probably label this with the steps that he's using. So this is, we'll start off with this. Let's make this blue just to be extra clear. And then this is going to be E1. And then, well, okay, so I've messed up the formatting, but you get the idea. So we continue. And then in step E3, we set M to 544. So we're setting M to N. Yeah, M to N. N to the remainder, which is 119. It is clear that if M is less than N originally, the quotient in step E1 will always be 0, and the algorithm will always proceed to interchange M and N in this rather cumbersome fashion. We could insert a new step at the beginning, E0, ensure M is greater than or equal to N. If M is less than N, exchange M and N. This would make no essential change in the algorithm except to increase its length slightly and to decrease its running time in about 1/2 of all cases. Back at step E1, we find that 544 over 119 is equal to 4 plus 60. Well, okay, terrible typing. 4 plus 68 over 119. Okay, fine. So R is 68. Again, E2 is inapplicable. So we continue. And at E3, we set M to N, and M, so M now becomes 119, and N now becomes the remainder, which is 68. And then we can continue this. I suppose we can continue without reading, just to get practice in. Not that this is super important, but useful to get some practice. Okay, so here we want to have m over n, which is 119 over 68, which is going to be, that's 119 over 68, so that's 1 plus, and then it's, I think it's 68 times 0.75, which is 51. So I think the remainder is 51. Let's check that in the text. And it is. Yeah, okay. So R is 51. Of course, I will need to start using some proper mathematical package at some point to not make this so annoying to do, I'm sure. Okay, E2, we continue again. E3, we set m to 68, which is the previous n, and then we set n to r, which is 51. And then we go through to E1 again. Now this is going to be 68 over 51, which is equal to 1 plus, yeah, so this is actually what I mean here is 51 over 68. 1 plus, and that's 17, I think. I'll need a better way to calculate remainder at some point. I guess maybe my little calculator has a modulo operator. 68. It does. Okay, perfect. That's great. So R is set to 17. E2 continue. Oh my gosh, this is tedious. I guess this is why we have computers to do this. And then M is 51. N is 17. E1, okay, 51 over 17. 0. Remainder 0. So at E2 we stop and we say that the answer, the GCD is N, I assume, 17. Let's check that. 119 over 17 is 7, and 544 over 17 is 32. Okay, great. So yeah, and this is confirmed by the text, 17. So this is an algorithm. The modern meaning for algorithm is quite similar to that of recipe, process, method, technique, procedure, routine, rigmarole, except that the word algorithm connotes something just a little different. Besides merely being a finite set of rules that give a sequence of operations, it's getting sunny, a sequence of operations for solving a specific type of problem, an algorithm has 5 important features. Finiteness. An algorithm must always terminate after a finite number of steps. Algorithm E satisfies this condition because after step E1, the value of R is less than N. So if R is not 0, the value of N decreases the next time step E1 is encountered. A decreasing sequence of positive integers must eventually terminate, so step E1 is executed only a finite number of times for any given original value of N. Note, however, that the number of steps can become arbitrarily large. Certain huge choices of M and N will cause step E1 to be executed more than 1,000,000 times. Now we have a bracket. A procedure that has all of the characteristics of an algorithm except that it possibly lacks finiteness may be called a computational method. Euclid originally presented not only an algorithm for the greatest common divisor of numbers, but also a very similar geometrical construction for the greatest common measure of the lengths of 2 line segments. This is a computational method that does not terminate if the given lengths are incommensurable. Another example of a non-terminating computational method is a reactive process which continuously interacts with its environment. How interesting. So a web server, I suppose, would be a computational method in a way. This is also, this is also an interesting distinction between two types of programs. The latter of which being certainly more difficult for beginners, reactive processes, although in a way easier to understand, in some ways easier to understand, but less easy to model. The reason I'm thinking about this is because I'm currently working on some curriculum for a company to do with test-driven development, and you end up with it's much harder to test reactive processes than it is, I suppose, algorithms, because you don't know if you've got to plan out all of the different interactions you have with them. 2. Definiteness. Each step of an algorithm must be precisely defined. The actions to be carried out must be rigorously and unambiguously specified for each case. The algorithms of this book will hopefully meet this criterion, but they are specified in the English language, so there is a possibility that the reader might not understand exactly what the author intended. To get around this difficulty, formally defined programming languages or computer languages are designed for specifying algorithms in which every statement has a very definite meaning. Many of the algorithms in this book will be given both in English and in a computer language. An expression of a computational method in a computer language is called a program. In algorithm E, the criterion of definiteness as applied to step E1 means that the reader is supposed to understand exactly what it means to divide m by n, and what the remainder is. In actual fact, there is no universal agreement about what it means if m and n are not positive integers. What is the remainder of -8 divided by -pi? What is the remainder of 59 divided by 13? What is the remainder of 59 thirteenths divided by 0? Therefore, the criterion of definiteness means we must make sure that the values of m and n are always positive integers whenever step E1 is to be executed. This is initially true by hypothesis, and after step E1, r is a non-negative integer that must be non-zero if we get to step E3. So m and n are indeed positive integers as required. Okay. So definiteness, yeah, okay. So that's an important factor. The steps must be defined, and I suppose he's making the point here that division is only rigorously defined, definitely defined, let's say, in certain circumstances where both the divisor and dividend, I think that's the word, are positive integers, which the algorithm in principle states up front. I'm not going to look back and see, but let's say it does, and assures through its working process. Okay. 3. Input. An algorithm has 0 or more inputs, quantities that are given to it initially before the algorithm begins, or dynamically as the algorithm runs. These inputs are taken from specified sets of objects. In algorithm E, for example, there are 2 inputs, namely m and n, both taken from the set of positive integers. Okay, so it has inputs. Output. An algorithm has 1 or more outputs, quantities that have a specified relation to their inputs. Algorithm E has 1 output, namely n in step E2, the greatest common divisor of the 2 inputs. We can easily prove that this number is indeed the greatest common divisor as follows. After step E1, we have m equals qn plus r for some integer q. If r equals 0, then m is a multiple of n, and clearly in such a case n is the greatest common divisor of m and n. If r is not 0, note that any number that divides both m and n must divide m minus qn equals r, and any number that divides both n and r must divide qn plus r equals m. So the set of common divisors of m and n is the same as the set of common divisors of n and r. In particular, the greatest common divisor of m and n is the same as the greatest common divisor of n and r. Therefore, step 3 does not change the answer to the original problem. I suppose this is a sort of casual form of some sort of proof. So after step E2, now what is step E2? No, after step E1. After step E1, we have, okay, so this is the relation, well, this is basically saying that if we divide m by n and we get a I don't know, something out plus a remainder, in which case we know that m is going to be some integer of n plus r. That's like the reverse of division with remainder, I suppose, is what he's getting at. And so if r is 0, then m is a multiple of n. Well, that is definitely true, because if this is 0, then we know that, you know, if m is going to be a multiple of n because q is an integer, because we've done integer division and with remainder. And clearly in such a case, n is the greatest common divisor of m and n. Well, it's getting kind of sunny here. Let me just close this. Okay, that's better. Okay. Right. And clearly in such a case, n is the greatest common divisor of m and n. Yeah, I guess that's got to be true, I assume. If r is 0, then I suppose he's combining this with the knowledge that we've just done this division to say that. Okay. If r is not 0, note that any number that divides both m and n must divide m minus qn equals r. So what I'm stumbling over here is I don't know how you divide, I don't know what to divide and this like equation means, actually. Let's write it down anyway. So in this case, what we're saying is the remainder is equal to m minus qn, which is true. And it must also divide qn plus r equals m. So the set of common divisors of m and n is the same as the set of common divisors of n and r. In particular, the greatest common divisor of m and n is the same as the greatest common divisor of n and r. Therefore, step E3 does not change the answer to the original problem. Yeah, I'm not able to follow that. What's the chat saying? Nothing. If you can write m as a times something and you can write n as a times something, you can write r as a times something. Yeah, I suppose that's true. Okay. Well, I'm going to note this down as something I would like to come back to and understand in more depth. This is a good example of a problem that, like, I think to understand this, to have understood this chapter, I will need to now I can't work my piece of software either. No, I don't want to redact it, actually. Where's the right thing? Is it here? Yeah, okay. Let's make that. Yeah, I'll come back to that. Okay, so some maths there. 5. Effectiveness. An algorithm is also generally expected to be effective in the sense that its operations must all be sufficiently basic that they can, in principle, be done exactly and in a finite length of time by someone using pencil and paper. Algorithm E uses only the operations of dividing one positive integer by another, testing if an integer is 0, and setting the value of one variable equal to the value of another. Those operations are effective because integers can be represented on paper in a finite manner, and because there is at least one method, the division algorithm, for dividing one by another. But the same operations would not be effective if the values involved were arbitrary real numbers specified by an infinite decimal expansion, nor if the values were the lengths of physical line segments which cannot be specified exactly. Another example of a non-effective step is if 4 is the largest integer n for which there is a solution to the equation w to the n, x to the n, y to the n summed equals z to the n, in positive integers w, x, y, and z, then go to step E4. Such a statement would not be an effective operation until someone successfully constructs an algorithm to determine whether 4 is or is not the largest integer with the stated property. Okay? We call that effective. Yeah, so there needs to be like sub-algorithms for anything which is not really basically done on a piece of paper. Let us try to compare the concept of an algorithm with that of a cookbook recipe. A recipe presumably has the qualities of finiteness, though it is said that a watch pot never boils, input, eggs, flour, etc., and output, TV dinner, etc. But it notoriously lacks definiteness. There are frequent cases in which a cook's instructions are indefinite. Add a dash of salt. A dash is defined to be less than 1/8 of a teaspoon, and salt is perhaps well enough defined, but where should the salt be added? On top? On the side? Instructions like toss lightly until mixture is crumbly or warm cognac in small saucepan are quite adequate as explanations to a trained chef, but an algorithm must be specified to such a degree that even a computer can follow the directions. Nevertheless, a computer programmer can learn much by studying a good recipe book. The author has in fact barely resisted the temptation to name the present volume the Programmer's Cookbook. Perhaps someday he will attempt a book called Algorithms for the Kitchen. That would be a different history, wouldn't it? We should remark that the finiteness restriction is not really strong enough for practical use. A useful algorithm should require not only a finite number of steps, but a very finite number, a reasonable number. For example, there is an algorithm that determines whether or not the game of chess can always be won by white if no mistakes are made. See exercise. Wow, it's going to be an exercise. That algorithm can solve a problem of intense interest to thousands of people. Yet it is a safe bet that we will never in our lifetimes know the answer. The algorithm requires fantastically large amounts of time for its execution, even though it is finite. See also chapter 8 for a discussion of some finite numbers that are so large as to actually be beyond comprehension. I was actually reading a Reddit thread about this today, about whether the fact that chess is not a solved game, which essentially means like you can't determine, like I actually was struggling to follow the conversation, but it meant something like you couldn't work out, like with tic-tac-toe, for example. The optimal play is defined. You know that you can always draw, or you can certainly in a particular situation, if it's possible to win, there is a set of step, like you know exactly what to move. But I think chess is not solved in that we don't know exactly what the right move for white or black is in every position. The chess computer, this surprised me because the chess computers tell you what they think is the right move, but something about them not necessarily being wrong, but like if you in theory, if chess was a solved game and white had an advantage, then you could know exactly what move to play at every point so that white always won. Like that would indicate it was or always drew, maybe something along those lines. I guess this is what he's referring to there anyway. I'm not a chess computer expert, so not yet. In practice, we not only want algorithms, we want algorithms that are good in some loosely defined aesthetic sense. One criterion of goodness is the length of time taken to perform the algorithm. This can be expressed in terms of the number of times each step is executed. Other criteria are the adaptability of the algorithm to different kinds of computers, its simplicity and elegance, etc. We are often faced with several algorithms for the same problem, and we must decide which is best. This leads us to the extremely interesting and all-important field of algorithmic analysis. Given an algorithm, we want to determine its performance characteristics. For example, let's consider Euclid's algorithm from this point of view. Suppose we ask the question, assuming that the value of n is known but m is allowed to range over all positive integers, will the average number of times Tn that step E1 of algorithm E will be, I'm reading this wrong. Assuming that the value of n is known but m is allowed to range over all positive integers, what is the average number of times Tn that step E1 of algorithm E will be performed? So if we have the algorithm, which I'm actually just going to copy out now, because it's annoying having to go back to it all the time. Okay, let's get this. Whoa, it's a bit big. Okay, can you see that? Yes, you can. Great. Okay. Where were we? Yeah, what is the average number of times, I guess average given, for a range of all positive integers, what is the average number of times that step E1, which is the division step, will be performed? In the first place, we need to check that this question does have a meaningful answer, since we are trying to take an average over infinitely many choices for m. See, that occurred to me as well. I guess it would be infinite, but I guess he's trying to make a point, I suppose, that there are, talking about which infinite it is can be informative. But it is evident that after the first execution of step E1, only the remainder of m after division by n is relevant. So all we must do to find Tn is to try the algorithm for m equals 1, m equals 2, up to m equals n. Count the total. Oh no, yeah, that's true. Doesn't matter how infinite m is because n constrains the number of steps. To count the total number of times step E1 has been executed and divide by n. Now the important question is to determine the nature of Tn, which is t in terms of n, I guess. Is it approximately equal to 1/3 n, or the square root of n, for instance? As a matter of fact, the answer to this question is an extremely difficult and fascinating mathematical problem, not yet completely resolved, which is examined in more detail in 435. Thank you. For large values of n, it is possible to prove that Tn is approximately 12. The natural log of 2, I think that's a natural logarithm of 2, times 12 divided by pi squared, multiplied by the natural logarithm of n. That is proportional to the natural logarithm of n with a constant of proportionality that might not have been guessed offhand. Well, that's quite so. For further details about Euclid's algorithm and other ways to calculate the greatest common divisor, see section 452. I'm sure we will have fun when we get there. Analysis of algorithms is the name the author likes to use to describe investigations such as this. The general idea is to take a particular algorithm and to determine its quantitative behavior. Occasionally, we also study whether or not an algorithm is optimal in some sense. The theory of algorithms is another subject entirely, dealing primarily with the existence or non-existence of effective algorithms to compute particular quantities. So far, our discussion of algorithms has been rather imprecise, and a mathematically oriented reader is justified in thinking that the preceding commentary makes a very shaky foundation on which to erect any theory about algorithms. We therefore close this section with a brief indication of one method by which the concept of algorithm can be firmly grounded in terms of mathematical set theory. Let us formally define a computational method to be a quadruple qi omega and f, in which q is a set, I and omega, I think it's omega, are, or is it? Yeah. Let me look that. Let me look that up before I go any further. Always saying the wrong thing. Omega, it is omega. Subsets of q and f is a function from q. Obviously, I'm not going to understand any of this, but I'll read it anyway. Is a function from q into itself. Furthermore, f should leave omega pointwise fixed. That is, fq should equal q for all elements q of omega. The four quantities q, I, omega, and f are intended to represent respectively the states of the computation, the input, the output, and the computational rule. Each input x in the set I defines a computational sequence xo, 1, 2 as follows. xo equals x and xk plus 1 equals f of xk for k is positive or 0. The computational sequence is set to terminate in k steps if k is the smallest integer for which xk is in omega, and in this case it is said to produce the output xk from x. Note that if xk is in omega, so is xk plus 1, because xk plus 1 is xk in such a case. I guess. Some computational sequences may never terminate. An algorithm is a computational method that terminates in finitely many steps for all x and I. Algorithm E may, for example, be formalized in these terms as follows. Let Q be the set of all singletons, N all ordered pairs, Mn and all ordered quadruples, Mn, R and 1, Mn, R and 2, and Mn, P and 3, where Mn and P are all positive integers, and R is a non-negative integer. This is wonderful to read. I'm excited for the point in my life where this will make sense. Let I be the subset of all pairs, M and N, and let omega be the subset of all singletons, N. So is he defining this algorithm in these terms? Maybe. I guess he is. Let F be defined as follows. F M and N is Mn 0 and 1. There's F brackets N for some reason, brackets N. Right, so are these steps maybe? So what is this? F. A function from Q into itself. Oh, it's sets, isn't it? Yeah, I don't know loads about sets, but I know the basic idea. It's a set of... if F is a mapping... F is a function from Q into itself, but a different element in the set maybe. So this is set theory related. I will need to learn set theory, I should think. I and omega and input x in the set I defines a computational sequence. I'm looking for a definition of I and omega, but I think it's not put here maybe. Well, anyway, I guess I think what I'm taking from this is we can define an algorithm as a sequence of mappings from one element in a set to another and ending up on the final one, which kind of maybe links towards finite automata maybe in my mind. Maybe. There's states, right? Maybe. Anyway, a very misty possible misunderstanding as well. The correspondence between this notation and algorithm E is evident. I'm sure it is. Oh, okay, right. Wait a minute. Okay. So this is the starting point, right? This is the starting point of the algorithm, because we go from mn to mn01. I don't know what the 0 means. Then we define, this is the step. And we're going mn remainder of m divided by n2, which takes us to the second step. We then have this. We then have this. And this takes us back to step 1. So is this like a kind of multiple dispatch in Haskell? Is that the right term? Maybe. Interesting. Maybe. How fascinating. Okay, well, maybe it is evident. Maybe it is evident. I'm sorry, Knuth, for saying, joking it wasn't evident. Maybe it is a little evident. It's a little evident, let's say. I don't know what this 2 is doing over here. I don't know. Maybe that's it's probably not a mistake, but maybe it is. This formulation of a let me see what the chat's saying. Maybe someone's got a bunch of tree. Yeah, that's omega. Omega, yeah, omega. We got omega right. First step. Okay. Okay. Right. This formulation of the concept of an algorithm does not include the restriction of effectiveness mentioned earlier. Now, effectiveness was... what was effectiveness? Operations must all be sufficiently basic that they can be, in principle, done exactly in a finite length of time by someone using a pencil and paper. Well, I suppose that's not a very rigorous definition anyway, so I suppose we don't mind about that. For example, Q might denote infinite sequences that are not computable by pencil and paper methods, or F might involve operations that mere mortals can not always perform. If we wish to restrict the notation of algorithm so that only elementary operations are involved, we can place restrictions on Q, I, omega, and F, for example, as follows. Let A be a finite set of letters, and let A asterisk be the set of all strings on A, the set of all ordered sequences, x1 through n, where n is greater than or equal to 0, and xj is in A for j within 1 and n. When n equals 0, this notation, etc., stands for the empty string. In general, it stands for a string of length n. I don't know what string means here, but presumably not text. The idea is to encode the states of the computations so that they are represented by strings of A star. Let n be a non-negative integer, and let Q be the set of all. That's got a name too. What is that? Sigma. Of all sigma j, where sigma is A star and j is an integer within 0 and n, let I be the subset of Q with j equals 0, and let omega be the subset with j equals n. If this one, which I'm going to have to learn all these letters mean as well, learn to pronounce them, theta. If theta and if theta and sigma are strings in A star, we can say that theta occurs in sigma if sigma has the form alpha, know that one, alpha, theta, omega again, alpha, theta, omega for some strings, alpha and omega in A star. To complete our definition, let F be a function of the following type, defined by strings, etc. There's another one. This is I forget what this one is. They're like upper and lowercase versions of the same thing. Phi. and all the integers, blah, blah, blah. If such and such does not occur in such and such, if alpha is the shortest possible string for which, etc., etc. Every step of such a computational method is clearly effective, and experience shows that pattern matching rules of this kind are also powerful enough to do anything we can do by hand. Pattern matching rules. Pattern matching rules are like replacement rules, right? So he's sort of getting a little bit close to talking about grammars as well, and we know that grammars are also related to the theory of computation as well, and are also related to finite automata as well. So maybe this is an interesting route into understanding this. I will, of course, once I understand this sufficiently, I will diagram all this out, at least for my own understanding. But maybe replacement rules. Are these just replacement rules? That would be quite something if they were. That would be quite something if they were. Shall we try it out? Let's try it out. If they're replacement rules, I can execute this reasonably straightforwardly. Let's find out if they are. Let's go with the trivial example from before. So let's go with 24 and 12 again, because we know that one terminates quickly. So let's say we start off with this. We apply the first rule. So that's going to be, I'll just call it across so we can move through this quickly. We apply the first rule to get 0 and 1. This matches against the second rule. So in which case, the next one is mn, and the remainder of m divided by n, m modulo n, so that's 24 modulo 12. Sorry, I'm making that, I've messed that up already. Maybe I put them in the wrong way around. Let's try the actual example from before. Let's try the one that he worked. 119 and 544. Okay. 119, 544, 01. And then let's work through that. 119, 544. And then this is going to be m, which is 119 mod n, which is 544, which gets us 119, and then we add a 2 here. Then we match against the third rule. The third rule says if r is 0, which it's not. So I should put this up here actually. This is going to be mn r, and I think let's call this I. Yeah. So if r is 0, something, but it's not, therefore we have mn 119 544. No, wait. 119 544 119 3. That's rule 3. Then we match against rule 3. Now this is going to be 544. No, wait. Let me get this right. Let me make sure I'm getting this right. We want n. 544. Then P is the third one. For some reason, that's P now, not R. That's fine, though. 119, 1119, 1. This is our new state. And then we work our way. We apply state 1. We apply rule 1. And so we get... here, we're going to divide m by n, which is 544119. That's becomes 68. And then 2. And yeah, we're just performing the algorithm, but in a with these replacement rules. And yeah, so that's the same. You can the reason I jumped to that is because we can see the same output here. How interesting. So this is his rigorization. This is his mathematical formulation of algorithms. I don't follow all of the notation, but I think I follow the idea that we're applying replacement rules, which we match against. We match against these on the left, and we apply this replacement rule on the right, along with these conditions, and we end up applying the algorithm that way. How? Well, yeah, okay, cool. And I guess then the thing that I'm not yet, I'm only have a vague notion of, is that maybe these quadruples are in some sort of set, or maybe the elements in them are sets. Or something. Yeah. That I'm a bit loose on. But that's an interesting idea. And I can follow it, I think, just about. Okay, cool. Cool. Okay. All right. General pronunciation, say 1,000, say hey, say... Okay, theta, I see. Okay, thank you, a bunch of tree. Theta, yeah, in general, any pronunciation tips are helpful to me. A lot of people don't like them, but my pronunciation is terrible because I just read stuff. Oh, really? Theta is pronounced with an E in British English, is it? British English, look at me. British English. So it's theta in American, theta in British. You learn something new every day. Here the 2 tuples seem to be input, 1 tuples are output, and 4 tuples are from Q. Aha. Yeah. Yeah, that would make sense. Q consists of the 4 tuples, the 2 tuples, and the 1 tuples. All right, so the set Q contains all of these elements. Is that right? Do I understand that correctly? And probably a bunch of other elements besides, we would assume. We're getting some rain coming back on the ambient recording. Now, where are we at? Okay, there's all this stuff about strings, which I'm not really following what a string is in this context. Think of it like an automaton. Q is all possible states. F is the transition rule from one state to the next. I and omega the input and output states. Aha. Q is the kind of universe of all possible values. Thank you, Yanchifim. Thank you, Tiny CLJ. Yeah, really, that's really useful. Yeah, like an automata, yeah. And I suppose he must be relating reasonably closely to Turing's work, you would think. He does mention Turing here. Every step of such a computational method is clearly effective, and experience shows that pattern matching of this kind are also powerful enough to do anything we can do by hand. There are many other essentially equivalent ways to formulate the concept of an effective computational method, for example, using Turing machines. The formulation above is virtually the same as that given by A.A. Markov. So it's Markov in his book, The Theory of Algorithms, later revised and enlarged by somebody else. Aha. At some point, I want to spend some time with Church and Turing, and there's the other one as well, but I haven't yet. The math will probably help. The math that I'll learn here will probably help with that. Okay, so we've got a bunch of exercises here, which I'm reasonably resigned to not being able to do most of. And we will probably switch to some math learning at this point, but after this stream. But let me just read through them and we'll see if anything jumps out as easy. Okay, the text showed how to interchange the values of variables m and n using the replacement notation by setting t to m to n, and n to t. Show how the values of 4 variables can be rearranged to b, c, d, and a by a sequence of replacements. In other words, the value of a is to be the original value of b. Right, I see. Try to use the minimum number of replacements. Okay, well, this one I can do. So we want to go from to... Yeah, so assuming we ignore any funny XOR tricks here, so I mean the naive solution would be just to go in with this, but we would lose the value of a there. So we like another naive solution would be to say t is equal. Yeah, let's in fact let's use the proper notation. Let's set t to be the contents of a, or actually now I think of it, it will be this one. We reverse. So we in the process lose the value of a. We can probably keep track of this over here. So so if we have a, and we're going to start off with all these values being good, and then we're going to gradually lose access to them. So we start off here, we'll move a, because we've lost a, we're going to have to put it back at some point. We know we've kept b is fine. We can set b to c, so b is now bad. We can set c to d, and we can set d to a. No, not to a, because we've lost a. We can set d to t, and we've lost d as well. So we're using a temporary variable. Is there a way to do it without a temporary variable? I don't think there is, and I think he's guiding us towards this. And they are in a cycle like that, right? A, B, C, D, B, C, D, A. Yeah, so I think this is right. Don't see any other ways of doing it. Let's flip to the answers and only read the answer for the one that I'm looking at. TA, AB, BC, CD, DT. Hey! Nice. Okay, got that one. 2. Prove that m is always greater than n at the beginning of step E1, except possibly the first time this step occurs. Well, I don't know about a rigorous proof, but we can probably look at it and see. Yeah. We can probably look at it and see... Try to make an intuition about it, but I won't look at the answer today. I'll probably come back to it once I know how to answer the statement prove, the verb prove. Okay, so prove that m is always greater than n. And we're going to have n be... n is going to be the n is going to end up being the remainder. And the remainder would be, we saw this earlier, right? We saw the remainder is Qn minus m. So I guess this is going to be... I don't know how to solve equalities. I was taught once, but I forgot. Now, intuitively, this would be wrong if we had like a really big number here. But it would be, yeah. Yeah. Well, I'm going to come back to that one. I guess let me look at it another way. So if the remainder, let me get rid of this. The remainder is going to be, the remainder is, let's say we're dividing n by n, then the remainder is going to be in the range of, it's going to be maximum. Yeah, if we're dividing by n, then r is going to be less than or equal to, no, it won't actually even be equal to, it'll be less than n, because it'll be in the range of n. So if r is less than n, we know that n is greater than or equal to r, and we know that the second time around m is going to become n and n is going to become r. So we don't worry about the original term of m, sorry. We know that this is then going to become this. Which is almost right. But I've got an equals there, and obviously that's wrong. So I assume when I inverted this, well, let me actually not invert it. What happens if I don't invert it? And I instead say, this is going to be n, and this is going to be m. Well, that works. So whatever my inversion there is too incorrect. Maybe. Or are we saying, prove that m is always greater than n at the beginning of step. Okay. Well, we know that the remainder of something is going to be less than the number we're dividing by. And then when we perform this replacement step here, we're going to end up with this from this. So I think that's why we know. I think that's why we know. It's not a proof, and it's a bit fuzzy, but I think that's what we know. And I'm also not 100% on the inequalities there. I don't know why my inequalities are wrong. Sometimes I did it. Okay. So something like that. I guess I'll check the answer and see if I'm along the right lines. After the first time, the values of the variable m and n are the previous values of n and r respectively, and n is greater than r. Yeah, so the correct logic. Okay. 3. Change algorithm E for the sake of efficiency so that all trivial replacement operations such as m set to n are avoided. Okay. No replacement operations. All trivial replacement operations. Okay, that should be plausible. Let's take this over here. For what it's worth, that's exactly the right idea. Thanks, Yanshafim. Thank you. Good to have a steer. Okay, so let's say we've got this. Now, if we were to put this in code terms, or at least in pseudocode, we're going to say r equals m mod n, if r equals 0, go to start. Sorry, no. If r is 0, return. Yeah, so we're going to go with a while true here. If r is 0, return n. Whoa, okay. Set m equal to n equal to r. And we want to get rid of this. In which case, we're going to set this to n. And we're going to set m to n. We might need to have like a double step here. So, okay, so let's say we start with this. Now, if r is 0, in fact, do we need to keep m? No, we don't need to keep m. So let's try this. If m equals 0, return m. Okay. Then we're not going to have this line. We've already got rid of m. So we've kind of swapped over r. I need a better way to work this through. A bit cognitively demanding this. We've already got r in m, and we've got n in n. So m and n have sort of swapped over at this point, or we've got Yeah, the meanings of M and N have swapped over, I think. So we've got R and we've got N, which means we now, I think, need to say something like this. And this is a bit of a guess. That's a bit of a guess. Let's try this out. And this is actually going to be N. Let's try this out. And let's see what we get to. So let's say we start off with 119 and 544 again. We set M to 119 mod 544, which is 119, and N remains 544. Not looking good so far. No, yeah. Okay, then we set N to 544 mod 119, which is 68. So 119 and then 68. Then we set M to 119 mod 68, which is 51. It's looking good so far. And this remains the same. Then we set N, which is 68, to, yeah, we set N to 68 mod 51. And that's, wait, which step are we on? I forgot. Oh no. That's the start. First operation, second, third. Yeah, okay. So we're setting N now. So 51 and 17. Now we're setting M. We're setting M to 51 mod 17, which is 0. Yeah, I've got a mistake there. And this remains 17. So actually we need to swap these over. Obviously, because we wouldn't want to return 0. I think this is right. Okay, so now I need to put this in the form that he puts it in. Let's assume the first section is identical. Let's go with E1. Oh, sorry, F1. Divide M by N and let R be, sorry, let M be the remainder. I've got it like straight in front of my head, don't I? Let me do this. Yeah, okay, let's go with this. Let me move this all to the right place. Divide by N by M and let M be the remainder. If M is 0, terminate. Yeesh. Need to get my boarding skill better. There we go. Okay, F3 divide n by m and let n be the remainder. F4 if m equals 0, sorry, n equals 0, terminate n is answer, and then F5 is like go back to step F1. I think this looks right. What's chat say? This looks better. Yeah, Tiny CLJ saw my error. Yeah, always return 0. Not a very good algorithm unless you want to get 0. Okay, what does the book say? 3. Algorithm F, Euclid's algorithm. Given two positive integers m and n, find the greatest common divisor. Divide m by n and let n be the remainder. If m is 0, terminates with answer n. Divide n by m and let n be the remainder. If n is 0, algorithm terminates with the answer m, otherwise go back to step F1. So same thing. Wow, got the right answer. I shouldn't be that surprised. Okay, great. What is the greatest common divisor of 2166 and 6099? Well, I suppose we use the algorithm. Which one do I want to use? I guess I'll use my new one. I feel very tempted to write a program for it. How many steps is that going to be? Well, anyway, it's just hard work, isn't it? It's not actually difficult. Okay, let's try it out. Okay, and we're gonna add a step here. My headphones are dying. Let me know if my audio goes weird at all. Yanchifim, yeah. So similar idea, yeah. Cool. Okay. Now I'm going to keep my head straight with the steps here, so that I don't make any horrendous errors. Okay. So I need to sort my window management out. Terrible. Okay, I'm just really resisting doing this because I don't want to do the work. Okay, but I'm going to do it. Right. Divide. So that's 2166 mod 6099, and we're going to set. Sorry, we're going to set. We're going to set this. We're going to set m to this, which we've already done. So that's the same. Yeah, I should have known that. 2166 6099. We can probably actually just omit that for brevity. Then we move to 3, divide n by m, and set n to this 1767. Then we go back to 1 and we divide m by n. That's 2166 mod 1767, which is 399. And we set m. Then we go to step 3, and this time we're setting n, so we say divide 1767 mod 399, that's 171. back to 1 again, and we're going to divide m by n. Which, yeah, that's 399 mod 171. And we're going to set m that, so that's going to be 57. Then we're back to 3, and we're going to set this to 171 mod 57, which is 0. So, sorry, mistake. So in this case, m is the answer and m is 57. Now let's double check this. 2166 over 57 is 38. 6099 over 57 is 107. Let's see. 57, that's correct. Okay, show that the procedure for reading this set of books that appears after the preface actually fails to be a genuine algorithm on at least 3 of our 5 counts. Also mention some differences in format between it and algorithm E. Okay. What are the counts? It's finiteness, definiteness, input, output, and effectiveness. And finiteness means that it will always terminate. Definiteness means like steps are simple. It's a good exercise, this. Inputs, it has 0 or more inputs. Important. Output means it should have 1 or more outputs. And effectiveness means... Oh, no, wait, that's the small steps one. Which means they take a finite amount of time. What's definiteness then? Definiteness, each step must be precisely defined. So, yeah, it's got to be precisely defined, and effectiveness means that it's got to be sufficiently basic. So it's got to be basic. Like, I guess, small steps. Yeah, okay. Let's look back at this horrendous algorithm then. Okay, so it has 0 inputs, which is fine. It has... Does it terminate? It does not terminate, I think. I don't think it terminates. No, it doesn't terminate, so it's not finite. It's almost certainly not definite. So 1 and 2 are out, and it has no output, and its steps are not, well, its steps are not basic either. But it does have an input. Oh well, I think that's that's correct enough. That's correct enough, I think. Let me get back to the right point. Not finite, nor definite, nor effective. Perhaps no output. Okay, that was the one that was in doubt. In format, no letter is given. Oh yeah, sorry, the format. Missed the format thing. Yeah, it's got no letter. as we've just found. Yeah. It's got no letter. It's got no little summary. It has comments. It's got no tombstone. It hasn't got this little summary at the top either. Oops, gone too far. Okay. No summary phrase, no tombstone. Okay. I'm just going to gloss the rest. I'm not going to do them, but I'm going to just gloss them just so I can prepare for the next stream. I'm going to end it around here. What's T5? The average number of steps E1 is performed when n is 5. Let UM be the average number of times that E1 is executed in algorithm E. If M is known and n is allowed to range over all positive integers, show that UM is well defined. Given an effective formal algorithm for computing the greatest common divisor of those integers, let the input be represented by blah, 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 blah. M A's followed by N B's. There is something about strings here. It is strings. It's strings but it's strings of symbols, like a kind of regular expression. True Odes fans will know that I've done some work on regular expressions before, and I was almost tempted to do some additional work on the recent developments of regular expressions, but then I realized they were beyond my current level of understanding of regular expressions, and probably not interesting enough to make a big video about. 9. Suppose that something computational methods. For example, C1 might stand for algorithm E. What's the question? Formulate a set theoretic definition for the concept C2 is a representation of C1, or C2 simulates C1. This is to mean intuitively that any computation sequence of C1 is mimicked by C2, except that C2 might take more steps in which to do the computations and it might retain more information in its states. We therefore obtain a rigorous interpretation of the statement, program X is an implementation of algorithm Y. Interesting. Okay. I don't feel as depressed as I thought I would reading these exercises. I feel like I may be able to approach a intuitive working of some of the mathematical problems. Not formal, not definitely not a formalized one, but I think I get the idea. But maybe worth doing some preparatory work. Okay, interesting. This has been a fun session. Yanchifim, I don't know how long ago you posted that, but yeah, thanks for tuning in. Thanks for coming along. Great. Okay. Well, I'm probably going to leave it there as well. Thanks for hanging out, everyone. And I will see you. I don't know exactly how often I'm going to stream these things, but I will stream them on a regular basis because I do want to get this done in some number of years that is not is less than or equal to the number of years remaining in my life. So that will take me actually streaming this. Yeah. Hope you have a good day, everyone. And oh yeah, I guess we should. When it's the advent of code streams, I usually do try to do some sort of raid, but I don't know what people who tune into this are interested in raiding into. Oh, you're very welcome, Tony CLJ. Thanks for tuning in. I guess we'll try. We'll see if anyone else is doing anything interesting in the software engineering streams, and we'll I will need to put my headphones in for this because this is a mega headphone. This will definitely feed back if I don't. Okay. All right. Who is doing software stuff? A lot of game devs on Twitch, as you'd expect, right? But game dev's not really my vibe. I mean, I like game dev. I've done a little bit of game dev. Oh wow, okay. C and shell scripting like it's 1979. Well, that sounds about right. Okay, interesting. All right, I think this is looking like a good stream. Okay, we are gonna raid Stian Hoyland or something. Sorry, I did an accent there. I don't know why I did an accent. So sometimes you read something, it just comes out in an accent. Okay, let's have at it. Have fun, everyone, and have a good rest of your day. Okay, ready. We're coming. We're coming. Got to press the button.